Okay. Yeah. Good morning, everyone.
Stand behind the
So,
desk. Stand behind the desk so they can see you online.
They can see. Okay. Good morning, everyone. So today, Mr. Diofer will present us his domestic PV payback analysis. So go ahead.
Good morning, everyone. I'm going to present the project Domestic PV Payback Analysis. PV stands for photovoltaic. My name is Teofur Gomez. I'm a student of electrical engineering technology in the pathway of alternate energy production. My advisor was Mr. Bill McGregor, and I want to give a special acknowledgement to Mr. Leger and Mr. Kudahi, because they helped me a lot to finish this project. Well, the agenda for this presentation is the following. I'm going to talk about my purpose of the project. Then I'm going to cover functional overview, technical description, going deep into detail about cost analysis and payback analysis, conclusion and future consideration, and after that, a small demonstration and space for some questions. Well, before going into the purpose of the project, I want to talk to you on my motivation. During taking the solar courses, I realized that solar energy production is something that is real possible for energy transition, and I wanted to get more knowledge about that. And also I wanted to know or to understand the financial aspects before these kind of projects, because well, a lot of people talk about energy transition, but I was wondering if this kind of systems are profitable or not, or is a good idea. I mean, if these projects are financial wise or not. So this project aims to answer these two questions. How much costs a domestic photovoltaic system here in New Brunswick? And what is the payback period considering government incentives? Here is an important thing to notice is that I'm talking about only for the province of New Brunswick, because the costs vary province to province, and also the incentives of the government vary province to province. So I want to be focused on this province and to meet the timeline for the project. Well, before going further to describing my project, I want to talk about what is a grid-tied domestic PV system and what is a net metering program. Net metering program is the program that allows to homeowners here in New Brunswick to install a green system to produce their own power and save money in the utility bill. The green project could be solar, could be wind, could be geothermal, but this specific analysis is based on photovoltaic system. So, and grid-type domestic PV system is when a house is connected to the grid and also connected to the photovoltaic system to supply the energy consumption in the house. So we can have different scenarios. For example, during the night, the solar system is not generating anything to the house. So all the house consumption is going to be supplied by the grid system. And in winter, for example, the energy production from photovoltaic is it's not very low, but it's lower than in the summer. Could be not cover the whole consumption in the house. So uh, the energy that comes to supply the house could be from the grid and also from the solar panels. And there are some spaces, for example, during the day that people are not in their houses, and the solar modules are still generating power. So in that case, that power goes to the grid. And the special equipment for this kind of system is the bidirectional power meter. What this equipment basically does is just the net metering, meter the energy that comes from the grid and the energy that is being exported to the grid. And at the end of every month, the meter do the math, and the utility company charge you basically the difference. Okay, so this net metering program has some requirements. As I told you before, this allows homeowners to generate electricity to offset the consumption. You cannot apply for this program if you're renting the house. You need to be the owner. The grid type domestic PV system cannot be more than 100 kilowatts. 100 kilowatts is a big value. A regular house can have a system around 20 kilowatts maximum, average. In your house, you will not want to install extra panels, for example, in your backyard, because it's not safe. It's not a good idea. So this value is pretty easy to meet. The 100 kilowatts. As I told you before, it requires a bidirectional power meter to do to measure the difference and the difference in power that you're generating and consuming. And also, you need to start the whole equipment that you install must be certified, and also you need to hire a licensed electrical contractor to do this, because if you do it by yourself, you're not going to meet the requirements to be connected to the grid. Maybe you can lose your money. So you need to show all the documents that certifies that your installation is safe and is properly installed. Also, you need to get the permits and the approvals before connect the system. You cannot connect and then go to the NB Power and say, hey, I got this system and I need to give this credits for this system, because they have to approve it before. They have to approve the system before. Well, this is my block diagram for the project. These are the two questions I told you that I want to answer. It's just the cost and payback time. I needed to do a data capture, also dimensioning a system, a solar system, then go to the cost analysis, then to the payback analysis, and at the end answer the questions and get to some conclusions. So this is the first two blocks in my block diagram. So these are the two questions, cost and payback time. I already talked about that. The site assessment to data capture that I did was, I performed a shading analysis, a house roof data, basically what I found, or what I need to find in the roof was the dimensions and the pitch, and power panel inspection. I inspect the panel. Well, what I have to say before that is that I use a typical regular house in New Brunswick to dimension a system for that house and to see with a real example what's the number for that house. And I measure the roof, I spec the panel in that house, and also gather some site data from Red Screen. Red Screen is the software available in the human in the energy resources website of Canada that allows you to dimension green projects like geothermal, wind projects, and of course photovoltaic projects. So I didn't build nothing for this project. I just used software and an Excel spreadsheet to get this to get the answers for these questions. These are the following blocks of my diagram. So with the data gathered, I was using the Red Screen to size the system, then create a list of materials to go to the market and get the data from the market for each material. And then with that price, calculate the incentives and the payback period for this system. And then with that information, I was able to answer the questions. And going to the technical description, I captured the data. These are the pictures for that. I performed a shading analysis, which is just verify if the roof is shaded for any building or tree, or because that can affect the energy production of the solar system. I did this with a sun path finder, but because of safety issues, I discussed with my advisor, and we decided that the best idea was not do any work at more than 1 meter of height. So I found that I can take the same data in a different location close to the house, because there is actually for this house there is no shade from any source. So I performed this analysis, and after that I measured the roof and inspect the panel. Basically, what I need to inspect in the panel is if there is a space in the panel to connect the solar system. After that, in few words, I want to explain how I did the dimensioning of the system. Basically, took a common panel from the market. I take its data sheet and its dimensions and just use the roof. Actually, there is an online platform called Pocket Solar that you can use to do this layout. So I found that I can install 24 panels. So I used this number to feed the information to the Red Screen. And with that information, I found that the system size could be 9.48 kilowatts, and with that system, I will show you later how much energy I can produce. So This graph shows the energy consumption in the house. As I told you, I use a real house and a real example. So I asked to the owner the utility bills, and I found the month by month the energy consumption. So this is the profile for the energy consumption in the house. As you can see, the energy from solar is only 58%. So putting with the roof full of panels, I cannot offset the full consumption. So these are the generation both month by month. As you can see, for example, in this month, this homeowner can have some credits in their power bill. So it means that this month, this homeowner is not going to pay nothing for the power bill because the energy production is more than the consumption. This is a list for the materials or parts or equipment for this system, and I went to the market and asked for the prices. It was difficult to find the prices because people doesn't want to give a lot of information. So the material was priced as $19,907, and going to the cost analysis, basically the cost analysis is to cost the whole project. So this value is the standard price of the system. It is the materials and including the labor to install the 24 panels, and these all the requirements for the net metering program. So I need to do a site inspection, actually 2 site inspections, one before go solar and then before install the system to verify if you fulfill all the requirements. And it's shipping, interconnection fee, engineering report, electrical permit, building permit. All these values are required to pay to meet all the requirements. So the purchase price for the homeowner is $31,212. So this answers the first question of the project. So this is how much could cost a photovoltaic PV system. For this house cost this. Another house could be a little bigger or a little smaller, so the price can change. Also, I need to do a payback analysis. So I need to find the incentives. So the incentives can be just from federal government and from provincial government. So federal government can give you $5,000 for any solar, any green project. In this case, it's photovoltaic project. So obviously you need to apply before in the website and fulfill all the requirements to get this money. I'm going to talk about this a little bit later. And the homeowner and the home energy system program is the provincial program, and the provincial program gives you $200 per each kilowatt installed. So you take this value, basically this value, 9.48 kilowatts multiplied by $2,200, and it gives you this value, $1,896. So the total grants or incentives are $6,896, and the net system cost, the new cost for this system, I mean for the same house, this is the price without incentives. If you want to go without incentives because you don't want to do, you don't want to go in that process, well, you pay this. But if you apply for the incentives, you pay this. Then I performed the payback analysis. The payback analysis is just to find how much time you need to recover the money. So, I mean, to get your money back. So I did some calculations, and I found that utility bill in the demonstration you can see. I would say that the utility bill savings goes to the 15,000, and this was the price that I showed you before. This is the without incentives. If you don't want to the incentives, you can go to with this price and have this net savings. So this answers the second question of the project, that is the payback time for this particular example is 15 years. But if you want to apply for the incentives, as I told you, you can get maximum of 5,000 from the government, from the federal government, and 1,896 from the provincial government. And additional, you have the option to apply for a 0% 10-year loan. Basically, if you want to reduce the burden of the debt, I mean the cash flow, if you want to have a better cash flow, you can use the money from the government. Also, you need to apply for the loan and get approved, and then after approved, get the money in your account. And with grants and incentives, the new price is this one, and there is a calculation of payback without the loan. Basically, the payback will be the same because the energy production is the same and the price of the system is the same. The new payback time for this new price of the system is 12 years. And using the 0% 10-year loan, comparing with this, is because the initial investment is not too high. Basically, the money is not coming from your pocket, it's coming from the government. You start to pay monthly basis the loan, but it would look like this. The payback time is the same, but the cash flow is better for the homeowner. So after 12 years, the system is being paid, and after that, start the savings, and the savings rise to the $33,873. There is not money coming to your pocket. It's this amount of money is the money that you're not giving to the utility company because you're reducing your utility consumption, right? So when you generate more power than you consume, you don't have a credit. You have a credit, but it's not a credit of money. It's not like you have some money in the MB power. You have some credits, the kilowatts credits. So when you have some kilowatts there, then you can use after that, after whenever you want. But you're not like having money in the utility company. Well, the conclusion is that I answered the questions about how much costs the system and how much time takes to recover the money. So, and as you saw, there is some savings, still savings, around $33,000 of savings after 25 years of the project. So the conclusion is that if you want to go in that way of energy transition, if you are interested to do that, it's something that is reliable, something that you can do, something also that you can use to save money from your utility bill, and something that people can start to do if you're thinking buying a house and took a mortgage. Also, you can think and to take this option to generate your own power and save money. For future considerations, I realized that I wanted to compare this project with another green project, like for example geothermal. So, and compare and see if it is better to go solar or go with a geothermal system. I would like to do that because there's another option, I think a good option, because geothermal systems are 250, 300% efficient. So I can say this could be a good option to go further with this project. I think that's all in my presentation. I'm going to demonstrate, to go with a quick demonstration with my Excel sheet. How can I change the?
You good?
Yeah, right.
I think you had it there.
Is that the, you have to change camera, using the camera for the laptop.
Anyone
No,
can
just
help me
wait
with
for
this
the
because
camera
I
to
set it
happen.
up before.
The camera will be back.
It's
Well,
like,
it's
that's
already-
a,
it's already,
it's just a reflection.
okay. It was. Well, to do a payback time calculation, first, as I told you, you need to size the system. But I'm not going to demonstrate this here because we need to, it will need more than 5 minutes to go open red screen and size the system using red screen. So, this is the information that I need to cost the system and do the payback and calculation. Basically, from red screen, you can have the system size and the general estimate annual solar generation. Basically, a payback time calculation is comparing the the price of energy consumption and the price of energy generation. Also, I need the utility bill data because I need historical uses per year in the house. I need the energy rate and also the system market data to price the system and estimate the energy escalation rate, which is a rate that the price of energy is going to increase year by year till 25 years. So after having this information and all the system materials required, I already showed this information in the presentation. So I called the system. I found the incentives and put this information in the Excel spreadsheet. Basically, I need to calculate the energy consumption, the solar generation, the energy rate, how it's increasing year by year, and to show you the summary is a utility bill. You will pay $107,000 for your energy during the 25 years, and the projected lifetime bill after solar is only $49. So with this information, I calculate this cash flows and basically found the information that I already give it to you in the presentation. So for example, if for a house goes only 9 kilowatts and 9 kilowatts. Obviously, the power generation could be a little less. As I told you, this information comes from the red screen. So I update this information if the system is different, and if the house is different, the energy consumption is different. So I should update this information, for example. And this project life electricity bill before solar is usually different, and the savings are different. For example, the new value of the system changes because the amount of energy that you're going to produce is less, you need less panels. So basically, that's the demonstration. That's what I did. I need to do my research to find the prices, to understand these financial rates, to show these results. So that concludes my demonstration. If you have any questions?
Yeah. Sure. What's the energy rate that you use? Is it the price you?
This is the price
pay
that
NB Power?
Yes.
Okay. Also.
This is the price from NB Power.
Okay. So means that you based your calculation on a fixed rate in 25 years.
Yes.
Right?
Yes.
Do you think it will stay the same during these 25 years?
No, it's not staying the same. You need to your energy escalation rate. Sorry, I understood wrong. you use an energy escalation rate, which
5% for your,
according to my research, that energy rate is increasing year by year. And according to my research, this 5% comes from the energy rate doubles its price every 20 years.
But you know that in April, we got, I think, almost 10% increase?
Yeah.
we were talking about it, yeah, that's what, I think they wanted that, they didn't quite get that, but they'll obviously apply for it again.
Yeah.
Still get what they want.
Yeah, there was almost a 10%, but it's special circumstances.
They're gonna get it, they just didn't get it all.
So
Yeah,
is
and actually, for example, in Toronto, the energy rate is higher.
Well, hold on there, you clearly stated this is a model for New Brunswick, so let's not
Yeah.
go compare Toronto there.
that's right.
Yeah.
Okay, stay within your boundaries and your scope, okay, and I'll stay within it too.
So that energy escalation rate, that's 5% over what period of time?
Every year,
Per year?
the energy goes 5%.
So you're accounting for a 5% increase per year?
Yes.
Okay, that's kind of what we want to know.
Yeah.
Yeah.
While we're on things like that, I was just curious as to why you didn't include labor costs also in your analysis, because obviously you talked about electricians and all that, but you never really clearly stated any labor costs.
I included labor cost, but when I did my presentation, I didn't include it.
Okay.
But it's this the cost for materials, and this is the cost for labor.
Okay, and where did you get that value? What did you use that?
I went with different companies,
Mhm.
footprint, solar with X, and Solar X, there's another company, and also companies or people that install panels like self-employed, and try to find these values, but it's not easy, but people give you the rate. So I was able to find some prices, and I tried to just like to use an average.
So those are all local companies they were? Or?
Excuse me?
They were local companies?
Some local and some companies from Toronto, but they apply the prices for New Brunswick. I mean, they sell projects here. They
Okay.
can quote projects for New Brunswick.
All right, so again, just for me, it wasn't apparent in here. Good. I like your use of Excel there. You've got a really nice Excel model there. That's definitely the way you want to do things. But for me, one of the things though that struck me, and I'm sure if Mr. Legier was here, is like there's a lot of what's in there. In fact, I think there's a lot that you could have done directly in Red Screen. Because Red Screen, the whole idea with Red Screen is to do exactly what you did. And if you purchase Red Screen, you can actually print out a report of it and the whole thing. So I'm just curious as to why you chose to do it this way as opposed to you had the tool there, which you obviously used to some extent, right?
Yeah, Red Screen basically do everything, right? Do all of this. But if I do just put numbers in Red Screen, I was not a good exercise for me to learn. So I wanted to take the formulas, the financial rate formulas, and do it here. And one test that I did for this project was comparing these results with Red Screen results, and find if I was understanding the right things with financial, the aspect,
What did you find?
financial aspect for the project.
What did you find from that test?
Uh,
Pretty close?
yeah, it was very close. So,
Alright,
What about the panels? The panels that were used, do you have any information on like what the model number and the characteristics of the panels?
yes.
What, maybe you had that, I just didn't see it.
These are the panel I used to do the simulation. Basically because I also talked with different companies.
Yeah.
And this, they told me that this panel has a good performance, and also is the distributors for this kind of panels are like they sell it in a good price and they can sell it in an efficient time. So the prices are very close, panel by panel. So I just took one to do the calculations.
Did you factor in shipping?
Yes. Yes.
One thing that's not on that little extract for me is, and I'm wondering if something you consider, as panels age, their performance decreases.
Yes, I include that part in the calculation.
Typical numbers 80%.
Yeah, the panel goes from 100% to 85, 80% after.
Typically 10, 20 years,
Yeah.
whatever it is, 10 years.
So I
is
include
that
that part.
involved in your calculations too?
Yes, here, solar generation.
Okay.
You can see the solar generation is decreasing
Okay.
along the life cycle of the project. Yes,
I saw on your panel data there, the word mono. What does that mean?
monocrystalline.
Yeah, what's that mean?
That
Is it
means that-
contagious? Yeah. Okay.
Well, that means that it's like a monocell to generate. I choose it because it's more fusion than polycrystalline.
Okay. What's the difference between a mono and a poly then?
This, what I understood is just the technology that uses to create the panel. So mono is it's like a round cell and to generate the power, and poly is like a square. And actually, I was reading the difference, but I don't remember.
Okay. Talking about efficiency, you referred to, thinking about comparison between solar installation as what you presented here and a geothermal, and you had mentioned geothermal being 300% efficient.
Yeah.
How is it possible to get over 100% efficiency?
Well, I'm going to use this.
Okay.
No, that's fine.
So for a geothermal system, let's say that this is the building, and you use a pump here. So you take the heat from earth to evaporate refrigerant, and that heat from the air goes to the building. So and also how can I explain? So you're taking heat from the air and also heating from the electrical system and put it into the building. So you're paying for this power, but you're getting more heating that you're paying because some power is coming from the air, and from the air is free. So the output power right? The output power is more than the input power. And the rate is around 3,000, 300, 250, 300. I was surprised when I saw this in my course, geothermal course, that how can a system could be 300% efficient? But it was real because you're taking energy from the earth, and that's the good thing about geothermal.
So is the output power actually more than the input power?
Yes. So,
You sure?
well, the heat, the energy in the building represented in heat is more.
You sure? It's a point of view here, it's a reference point, right? It's a reference point. If you look at it physically, in physics sense, is P out truly larger than P in? Can it be at a physics sense?
Well, let's not do this. It's not the power; it's the energy. So
Well,
Energy and power are related by time, so.
yeah,
But it's not your P out, it's your P in. Which P in are you using?
P in.
Which P in are you using?
Yeah, because you're not showing everything there in the equation, right?
You're using P in that you're paying for.
Yeah, the electrical.
That's the point of view you gotta remember. Yeah, exactly.
The
It's
electrical
not
power.
truly the P in of the system, it's P in that you're paying for, which makes sense. I mean, that's, the financial sense makes, but you gotta be clear that you explain that,
Yeah,
Yeah.
because no system can be more than 100% no matter what.
that's right. In an electric baseboard, you're paying for all the energy that goes into it, right?
Yeah.
100%.
Financial wise is 300 efficient, but electrical, no.
Exactly.
Okay,
You
yeah.
gotta be careful, that's a little of a sales trick.
Yeah.
Right? You're not bending any rules of
Thermodynamics.
Yeah.
One short one.
Just one.
Yeah.
Can you include the interest rate in your calculation
For the loan,
for the money, yeah?
no, because the loan is 0%.
No, for the whole system, did you include, because like $1 today is not the same 20 years.
Oh, inflation.
Yeah.
Inflation, yeah.
Yeah, the interest rate.
Inflation.
Yeah. It's just a comment.
No, because I was not calculating the net present value.
It
Was just calculating the payback time. And inflation, you buy the system today
Yes,
and you,
because you subtract that at the end. Like, I saw you like you cost 31,000, at the end you're saying, okay, 58,000 minus 31,000. So maybe you should like, think about it for future or something.
okay. And inflation not because you pay the system today and you just put the,
Which means,
Doesn't matter, at the end, you're spending money, you're saving money at the end,
not today.
which is not worth as much dollar-wise
Yeah,
as today.
but I
So
use
you
the
have to-
installation rate for that. The installation rate for the price of the energy.
No, it's not ridiculous, we're
It's
talking
not
money wise.
Yeah, we're talking money here, purely money. Okay?
If I gave you 1,000 today, we'd be probably
Yes.
3,000 20
In the
years from
future.
now.
But I just wanted to calculate the cost and payback.
Well, just a comment is.
Okay, thank you.
Thank you.
He was right.
Very good.
Presenter 21 of 38. Community service. Community service. Anything online? What do I have to do? What sucks about
You've seen this? Basically, you're going to do those drafts.
No, I've seen yours. I literally like very proud of I don't like it. I don't love
You'll see what he wants to see. We're all set to go around 9:30. Good to go. Okay? Yep, yep.
the mom will come over and see all the doctors come by.
Like, everyone liked it, everyone had March, we all really cool, like, seasons of the technology, guys are really going in with you.
So I started to figure out ways of parking without that car. What? I think it's just take over the car, so I had to like play around.
Otherwise, it's like, yeah, it's a little awesome, I always come up with like,
I see the video the other day, and it was literally a goose, and like standing around and sort of how yeah, all the time.
No?
Yeah, and then I bring it up.
I want my birthday candle. What about it? No, yeah, if you take all the lemons except for one, average, yeah. All of them are equal together. So, here's the question. You're off. Yours? Yeah, you could. Yeah. Yeah, maybe this one has yeah. Probably do you want to do introduction? I mean, like, yeah, anytime. Yeah, it's 9:29.
Okay, now it's time for Yamju Lor to present her project entitled Automated Water Level Controller. It's all yours.
So So, hello everyone, my name is Yamjala and I'm taking the alternate energy pathway in the electrical engineering program. So today I'm going to present my project which is an automated water level controller. So before I proceed, I just wanted to let you know what I'll be talking about during the presentation. So the first thing I'll be talking about just a brief introduction on what the system is about, and then I'll continue with the objective to why I designed this project, and then the next thing we'll look is how does the system work, and we'll also look at the different diagrams, which is the concept, the schematic, and the block diagram. We're also gonna look on the applications of where this type of system can be used, and I'm also gonna discuss about the components I use in this project, and then I'll also be talking about the problem I encounter and the recommendation, and then we'll conclude the presentation from there. So. Now we're looking at the objectives, so why I decided to design this project. So the first reason is for efficient water management. So this is just to minimize the water wastage and prevent overflow or dry time. The second reason is the time and labor savings. This is to avoid the manual monitoring and control of the system. The third one is to increase productivity. So this is just to ensure a constant supply of water in various applications, whether in irrigation or industrial processes. The fourth one is energy savings. This to optimize the pump usage and then reduce the energy consumption. And the fifth one is to prevent equipment damage, to avoid the burnouts of the motor and the failure of the motor by dry run. So the next thing we'll look is how does this system work. So basically, we have the two major sensors, which is the first one is the float switch sensor that detects the water when the level is at the very bottom of the tank and allows the system to energize the pump, and then the pump starts filling water in the tank. And then we have the other sensor, which is the one at the highest like the top of the tank. So this is when the water reaches the highest level, so it triggers the pump to stop. So we have the control unit, which is in this case I use this as an IC. This is the one that analyzes the signal and triggers the pump accordingly. So when the water is low, and then when the water reaches the highest level of the tank. And we also have the sensor control water flow, which is responsible for filling and drainage of the tank to maintain that desired level. The next thing we'll look, this is the concept diagram. So we have, so in this design I use to show 4 levels. So we have the lowest level, we have the second one is the mid-low, the third one is the mid-high, and then we have the highest level. So on the control unit, where we have the different levels. So we have the LED indicator that indicate the different levels. So we start from the 25% to the 100%, which is the highest, and the 25%, which is the lowest. and then we have the main tank. So this is the main tank is where the levels are going to be controlled, and then we have a secondary tank, which this is where if you want to use the secondary tank to fill the main tank, and then the pump is placed inside the secondary tank, and then and then the pump pumps the water or liquid from to the main tank, and then we have the pump connected also to the controller. So we'll move to the second diagram, which is the block diagram. So on this system, I'm using two 9-volt batteries. So we have the first battery is used to supply the IC, and we have the switch to switch it on and off. So we have the float sensor. So the float sensor sends the signal to the IC when it's low or when it's high, and then from the IC, the IC sends the signal to the relay switch for the contact to close to fill the water, and then the contact also opens to stop the pump from filling the water. We also have the LED indicators that indicate, like I showed on the previous slide, different levels. And then we also have another supply now to supply the pump as well. So we'll move on to the schematics. So before I start, I just want to let you know, I actually uploaded the wrong version, because during the design, because I draw this one on AutoCAD, so it's different with the one I use on KiCad to design the PCB. And then I did some modification on the top, on the terminal block, the first terminal block. So the pin 2 normally is connected to the ground, and the pin 1 is connected to the switch, from the switch to the resistor, from the resistor to the LED. We have the terminal TV2 is the second terminal block. So this is where the main sensor responsible for the triggering of the switch is connected. So on pin 1, I use one end of the sensors to connect, like it's just like a common connection. I use the second wires of one of the sensors to connect on pin 2, and the second wires of the second sensor to connect it on pin 3. And then the TB5 is just the same connection, but that one is for that shows that indicates the two middle levels, so the mid low and the mid high. And then we have the IC used is the NE555 IC. So we have on the pin 8, is connected to the supply, and then with the pin 4, which is the reset button, the reset pin is connected to the supply as well. We have the pin 2, which is the trigger pin. This is the pin responsible to trigger the relay when the water level is at its lowest. And then the pin 6, which is the threshold pin, is the one responsible to trigger the pump to stop when the water reaches its highest level. The pin 5 is the control voltage. So from the data sheet, so the reason why I also connected the capacitor is for the voltage reference, because in the IC there's a voltage divider that's happening in IC because it has 3 resistors. So by connecting the capacitor on pin 5 is to eliminate any high frequency noise. to also ensure a smooth supply of voltage in the IC. We have also the transistor there. So the pin 3, which is the output, the pin 3 is the output of the IC, is connected to the base of the transistor. The emitter is connected to the ground, and then the collector is connected to the diode. And then the diode is also placed across with the relay, just to prevent any reverse current when the relay is energized. And then the TB3, that's where the pump is connected, and the TB4 is where the second supply, which is the 9 volt, is connected. So the same reason I also place a capacitor there to also eliminate the high frequency noise and any ripple. And then I decided to also use different LED colors for understanding. So the lowest level has a yellow LED, the highest has a green, and then the 2 middle ones has a blue LED. So we'll move now to the applications, like where this type of system can be used. So we can use the system in the domestic water tanks to ensure a steady supply of water in homes, and then it can also be used to in houses with a hot water tank. So let's say you want to, since the hot water tank gets the cold water, and then we also need a specific amount of water in the hot tank. So we can also use the system to avoid the overflow of water or shortage of water, to have a constant supply of hot water. The second application is the irrigation system. This also can be used in agricultural purposes, and supplying water for the farm, and then because the farm needs a constant supply of water to ensure the chain is maintained, the production chain is also maintained. So the third application is the industrial processes. So this also can be used. This type of design can be used in the control of liquids in a tank. So not necessarily water, any liquid in a tank, and then the manufacturing plant or industrial applications. The fourth one is also can be used in water treatment plants to monitor and control the water levels in filtration and purification processes. The fifth application also can be used in swimming pools to also avoid the overflow of water and then maintain a desired water level. So the next thing we'll look now is the functionality of an automated water level controller. So this design can use either the float sensor or an ultrasonic sensor for the detection of the levels, and then you can also, as a controller unit, you can use a microcontroller or a PLC based programming to process the sensor inputs. And then as actuators, you can use devices that controls the water flow, such as the solenoid valve or the pumps. So now we'll look at the components, the main component used. So the first one is the NE345 timer. So I decided to use this IC because of its configuration as an unstable mode, which produces a continuous oscillating output signal with a specific frequency and duty cycle. So also this IC generates a timing signal for various operations in a water level control system. The other reason for the pulse is the pulse generator. So this type of IC generate a precise pulses of fixed duration, which is also crucial in controlling the timing of the different events within the water level controller. And then which is also used to trigger the relay switches or activate solvent microfilling and then drilling of the water. Well, the next thing we have the relay, which is an SPDT relay. So we can see the switching capability of the contact is maximum is 50 amp. We have the configuration of the relay. Also, it's an environmental friendly product, and of course, it can also be used on the designing of the PCB. Then the next component is the water pump. So this is just a simple water pump. We have a voltage. It can run under 6 to 9 of voltage, and then they have the current produces a 150 to 250 milliamp current, and then the top inlet is where the water goes in the pump, and then the second inlet that looks forward is where the water leaves the pump. So, and then they also have, at no load, this pump can operate, can fill 100 liter per hour. But if this is at no load, so if you connect the pipes and all that can also change the operation of the pump. The next now is the float switch sensor. So we have the specifications, the working current, which is 3 amps, the working voltage, and then so just this sensor, how it works is like the little round, the round thing. So when it goes up, the outputs 1, so that outputs a signal. And when it's down, it outputs a 0, so that means there's no signal. And then this sensor can be used on the working temperature of 30 degrees to 80 degrees Celsius. And the maximum temperature it can operate in is 85 degrees Celsius. So we'll move to the next component. So this is just a normal 9-volt power supply, but in my project I didn't use the plug adapter. I just used the wires to connect on the terminal block, and yeah, just a 9-volt battery. So now we'll look at the problem I encountered during the designing of this project. So the first problem I encountered was the capability to stop the pump automatically when I test on the breaker. So I run out. I had this problem, and then until I realized with the help of my advisor as well, and then we realized that the connections of the ground pin, the connection of the ground pin of the supply and the relay wasn't connected on the same ground. So this is why I had that problem until we realized that the ground wasn't connected on the common ground. The second problem I encountered was I had so the relay would click, but the pump was not energized. So yeah, it was just a connection issue that I had to double check. I have to double check. So, but the second problem was actually the first problem I encountered when I figured out the solution, and then I had the other problem as well. And the third problem also, doing the designing of my PCB. So I had when I had everything soldered and all that, and realized that the pins, the pin 2, the pin 3 of my IC was short-circuited because the traces for those pins were on the top layer, which is the ground plane. So it when soldering, part of the solder iron went on the ground plane. So, and then after when I did the continuity test that I realized that was the issue for my project not working. So the recommendation. So actually, the designing of this project was for me to gain the knowledge behind that, because we have the same system where I came from back home. So, but I had no idea actually how everything was, like how the pump and the system works, and then and also the one we use back home is a PLC-based system. So, but for me, I wanted to gain the knowledge by doing a small-scale system, and then later on with the knowledge again on the PLC course that I took it, I could also design the same type of system, and then it just works more. The PLC work more with the relays. So. So to conclude this presentation, so yeah, the main objective of this project was to efficiently manage the water, either in a house, on a domestic home, or as an irrigation system or industrial processes. So also during the designing of this project, I had to select. I was first of all selecting my component just based on the voltage, but I also realized that there's more to look at when selecting the components. And then yeah, for future implementation, I would also like to use a PLC based project. So unfortunately today I won't have any demonstration, because like the problem I still on the problem I encountered on the PCB. So the soldering iron was also the soldering iron was connected on the pin 2 and 3, which is the main which is the trigger pin, and then the output pins. So I tried to remove the soldering iron, but unfortunately I couldn't get every solder, like, because that's also where the ground plane was connected. So I tried to remove with different options I had in the lab, but I couldn't like completely remove it. So, and then also my transistors, when I was also soldering, the pin, the emitter which is connected to the ground, and the base pin were also also touching each other. So that's why I try to remove the solder as much as I can, but it was still short circuited. And then I still wanted to like at least do a demonstration today, so I ordered another PCB outside, but unfortunately it came late. So that's why I'm not able to do a demonstration today. But at least I just wanted to just show the enclosure and then how it was going to work. So before I proceed, during the designing of the PCB, the terminal block, I think terminal block 5 that shows the 2 middle levels was omitted during the design of the PCB. So when I will show the casing, we're just going to see the 2 levels, which is the more important levels that's responsible for the triggering of the relay. And then we also have the side pages that I use for the pictures as well. I'm seeing the video on the screen, it's not showing.
What you have to do is you have to end the PowerPoint show first.
Oh.
So go to the upper right and click the X. There, now you're good.
So yeah, this is what, like I showed the concept diagram, this is what the sensor is coming out and then placed in the tank. And then here we have the switch to power on and off the system. And then that's here we just have the highest level and then the lowest level. So this one is the lowest I used like I said, the yellow LED, and then this one I used the green LED, and then this is the LED when you power on and off. So I just wanted to show how the enclosure was gonna look like. And here we have here to connect the 9 volt for the pump, and then here to connect the 9 volt for the supply. And also one thing I didn't mention for the future implementation. So while designing my PCB, I also make sure to have a smaller PCB so that I can include the battery in the casing, so that it's easy for the user to also to carry, easy to carry, and then to also keep the control, the system, And then also the sensors for future implementation. I also would like to use a different sensor, like a much longer sensor, so that it's easy to place and then to measure, easy to place in the tank or where you want to measure the levels. So. So that's everything for my presentation. Open for questions.
Could you bring up your schematic, please? All right. What configuration is this in?
Sorry?
The 555 timer, what configuration is it in?
It's a stable mode.
So what does that mean? What does a stable mode mean?
So that means it's it sends a precise timing pulse.
It senses a precise timing pulse. When we talk about a 555 being in a stable mode, what do we mean by that?
I think because stable, that means it's configured to
If it was stable, what would that mean?
Let's start with the word stable.
If it was stable, what would that mean?
Yeah.
What would the output look like if it was stable?
the output was is not going to be like the precise pulses.
Don't use the word precise.
Yeah.
What's stable mean? Just define stable for us first, okay?
Well, even what two conditions can the output be?
Of the
555. Yeah.
Of its output.
What two conditions can it be? Can it be, you have 9-volt batteries there, can it be 0 and 2.5 volts? Can it be 0 and 5 volts? Can it be 0, 0.1, 0.2, 0.3, 0.0 up to 9 volts?
No, it will be it will be 0 and it will be 0 and 9 volts.
Okay, so two conditions. So if it's in a stable state, what does that mean?
Not astable, but
stable.
Stable
Yes.
state,
Yes.
right? What does that mean?
If it is stable.
If it is stable.
What does that mean for the output?
So that means the output will be 0.
Or it could be 0, yes, but it could also be the 9 volts. And what? If it's whatever condition it is, if it's stable, it will want to. Will it want to change?
No.
No. So that's stable. So if we add the letter, the prefix A to stable, what does that mean?
So that the output's gonna change.
That's right. It doesn't want to stay in the state it's in. I used to have a cat that was astable because it was always on the wrong side of the door. It drove me nuts. Okay? So this is astable. Okay? So it means that when it's in one condition, it wants to go to the other condition.
Yes.
The other condition it wants to go to, so then it will, what? What do we say?
Yeah, what's the word that
What's the word we
describes
use?
that?
If you're going from one condition to the other.
To toggle. To
Toggle, yeah, toggle means a change, but if it changes continuously. We have a signal that's changing continuously, like a sine wave or a square wave. We say it starts with an O.
Is it start with what?
Starts with an O. It
Oscillating.
so it's oscillating. Is that what your system does? Does it oscillate? Does the output oscillate?
Yes.
It oscillates all the time? So
Uh,
your relay's oscillating all the time?
No. It just changes.
So it tends to be in a stable state.
Mhm.
So we can't call this an astable condition, right? You said it was configured as an astable multivibrator. It's not.
It's not, yeah.
And I could have told you that right away because you are missing a few components that are crucial to that, which typically are called RA, RB, and C.
Well, that was my next question. If it is astable, what sets the frequency and the duty cycle? But I don't think you can explain that here.
On pin 6, right? Pin 6, you have a capacitor there, right?
Pin 5.
Pin 5, oh, that's the wrong one then. Oh, that's the voltage. But you should have one on pin 6 also, okay? If it was astable, it's not, okay?
So what mode is it actually operating in then? If it's not astable?
Stable.
There's another prefix that you need to add to the front of the word, okay?
Monostable.
Is it monostable?
Monostable means it would be only one to stay at one state. If you push it to the other state, it would always come back to one state, right? In your case, it's stable at both states. So what's the word for that?
I said stable. You said another way to say that.
Well,
There's a prefix you're missing there.
Starts with a D, yeah?
Don't tell her what it ends with.
You said start with what?
Huh?
You said start with what?
With a B.
A D.
Oh,
B,
B.
bravo. B is in bravo.
Oh, bistable.
Bistable. Right.
Okay, so that means that whatever state it's in, it will remain there unless it's forced to go elsewhere. And when it's forced to go elsewhere, it'll stay in that state. Okay? So this is a bistable multivibrator. Okay? So how does that work then with your water sensors to turn the pump on and off? We know it wants to stay in one state or the other. So how does that work?
So basically the pin 2, which is the trigger pin, So when the sensor detects the when the sensor is below, doesn't detect any the water, so it will send a signal to the IC, and then
Does it send the signal? What is your sensor essentially?
it's a float switch.
Yeah, so it's a switch, right?
Mhm.
So either it provides what, a voltage, it applies a voltage
Mm.
or not, right?
So it provides a voltage across the pin 2,
Yeah,
and then the IC because the IC will it measures the possibly one third of the supply voltage. So the IC will send the voltage to the
oh, it won't send the
Uh,
voltage don't get sent.
the voltage will go across the transistor, and then from the
Okay,
transistor.
but why does it do that? Why does it do that? You said that, you know, you get a voltage across TR pin 2,
Mhm.
but there's, whether it's 0 or 1 dictates what's going to happen at Q, but it's
Mhm.
compared to what?
To the threshold pin.
Okay, so what does the threshold input do? It varies what?
What do you mean?
Well, the threshold, does that stay static?
Well, on the threshold there'll be 0 volt.
All the time?
No. Until
If it was 0, we just tie it to ground, shouldn't we?
no.
Well, if we wanted 0 volt, we just tie it to ground, so it's not.
So from the pin to the trigger pin.
All right.
Because
let-
in the IC also there's the like a voltage divider
There's a
happening.
voltage divider, yeah.
So
There's something else there too. There's a voltage divider. There's also 2 comparators.
yeah, the GK flip flops.
Yeah, no. There's 2 comparators. I don't know if there's JK flip-flops. Anyway, those comparators though, the relationship between them dictate what's going to be provided on the Q output. Right? There's a flip-flop after one of the comparators, the latch. Okay, but there's 2 comparators, and that's the key. There's 2 comparators across a voltage divider.
Yeah.
Okay. Let's just quickly TB3. What connects to TB3?
The pump.
The pump. Okay. And so I'll just note here, you have D2 across the relay there, the coil of the relay to protect what?
To protect the relay and the other parts and the
No,
other.
the D2 doesn't protect the relay. What does it protect? Yeah, there was a discussion about this yesterday, twice or 3 times.
Yeah.
It protects the other components,
Which component specifically?
the transistor.
Okay, so on the other side, we have a pump, which is a coil also. Okay, that's gonna get switched by the relay. How come we don't need to protect things there? It's another coil. And if we do, what needs to be protected? You have a pump that's a coil there.
Yeah.
It's gonna get switched on and, more importantly, off, okay? Same thing like the transistor is switching the other coil on and off, and we need to protect the transistor. So what needs to be protected on the pump side when the relay switches on and off? What acts like a switch on the pump side?
The contact.
The contacts. So we should have a diode where?
On the other side of the relay.
Yeah, where? Across what?
Across across one pin, one end of the contact, and one end of the contact and the pump.
Which end of the contact? Be nice if they were numbered.
Well, they kind of are in the terminal.
Yeah, I guess they are. It should go across the terminal block. Because if you don't, what's gonna happen to those poor contacts?
It's gonna be damaged.
How? What's gonna happen?
The core will get too hot.
Too hot? No. The high voltage potential generated by your pump is gonna arc across your relay contacts and it's gonna pit them and they will expire very quickly. Arcing is electrical conduction, right? It's breakdown. Okay. Yeah.
You hogged it big time. Anyway,
All right.
I guess we're at a time.
Thank you.
She doesn't have a lot of
Okay.
That's why I think it's low.
I have ate my dinner.
Yeah.
Yeah, I don't think you need this. I just, no, you can take it. You will take the camera. Yeah, because I know you just can't see it. Still got 10 minutes. Yeah.
Multiple classes at the same time. I haven't mastered the art of being in two places at the same time. I'm working on it, but
What's taking you?
that's that.
What's taking you
Taken.
so long?
Oh, structuralists.
Oh, yeah.
Structural engineers.
Yeah.
But I did cut that class off an hour early. So I'm doing my best.
No, I meant what's taking you so long to adopt that skill?
I get it.
Yeah.
Yes. I've been trying to figure that out, and I've even woken up in the middle of the night by frothing at the mouth.
Yeah.
It's really, I don't know why it's hard.
It's hard, eh?
Yeah, I know, for some reason.
Yeah.
If I move,
You gotta stay behind the desk. Yeah. Basically. You need to do a demo though.
Yeah. But I have a video, and then I'm gonna bring my camera so that they can see.
Yeah, if you point that camera over there, it should be
Yeah.
fine.
Well, does it have a long cord or no?
Whatever the cord is that's on it. I mean, there are USB extension cords.
I can try remote, like turn my desk when
What you
I.
could do is, you're demonstrating this?
Yeah.
I think if you just turn it over, I mean, you can see what it's gonna be. Yeah.
Oh, how are you feeling? Crackers? Ready to, do you want to 100 meters? Ready to I should have brought some of those blocks. So relax, have fun. That's my job. I told them all to ask you super easy questions. And they all just glared at me when I did that, I interpret the glare as their focus. True. There's that minor detail.
Is this yours?
Like it is. Your eyes. Maybe the camera.
Everyone actually are sitting here.
Yeah.
Yeah, I know. Translation
I think I'm gonna finish. One thing
Well, I thought we could just leave it there and you can just prop it against it, you know? Like I can just bring it and I'll move my body like this and then it can lean against that.
Yeah, maybe. Yeah.
I'll be back. Got locked someone.
You sit up there, George, you have a smile on your face. Of course.
Stand behind the desk when you talk.
So before we start with the next presentation, we just would like to welcome our guests from NAV Canada. They're sitting over there. That's MD Godet and Mr. Andrew Estabrooks. Okay. And I think now it's time to let Hayley McFarland present her thermal energy storage sand battery.
Alright, hello everyone. My name is Hannah McFarland and I'm in the Electrical Engineering Technology program, specializing in alternate energy systems. As Mr. Salal said, I'm going to be presenting my thermal energy storage for a sand battery, and I did an analysis project for SPL. I would like to thank my advisor, Mr. Salal, for helping me so much throughout this process, and I really appreciate his guidance. So, what I'm going to be talking about today throughout my presentation is what exactly is a sand battery? Why is this important? How did I build my sand battery? How did I collect data for my analysis? My analysis conclusion, how this technology can be implemented, and I have a video demonstration as well as a build demonstration for you guys as well. So, first of all, I wanted to talk a little bit about what exactly is a sand battery. If most of you are like me and you hear this term, you might be unfamiliar with what it means. Like I was when I was researching topics for this project. I wanted to explore a little bit in different topics that aren't as talked about in alternate energy systems. And I came across an article talking about a sand battery. So a sand battery is a high temperature thermal energy storage using sand or sand-like materials as its storage medium. And it stores energy as heat within itself to be used in later times. So, a little bit of background behind the sand battery. I have a picture of these two gentlemen here, which have really hard names to pronounce. They are the CEOs and the engineers of a company called Polar Night Energy in Finland. And they are the ones who have come up with this idea. So when they were graduating university, they wanted to start a hippie commune. They needed a way to be able to store their energy they were producing by their renewable sources, and they were trying to design a system to be able to harness this. They had come up with this design of a sand battery. And when they got talking with people and sharing this idea with their teachers, they realized there was a great demand to produce this commercially and for it to be used not just within what they thought they wanted to do as a hippie commune. So in this picture here, this is the real life version of a sand battery in Finland that is being used today to provide heat for their indoor swimming pools and to heat their communities and their buildings. For my project, I obviously could not build a battery at this scale, so I chose to create a smaller scale, and for the scope of my project, I'm going to be testing the theory and not so much a build to be able to provide heat to something, so my battery cannot actually function as well as the larger scale that they build can. So a little bit about how sand batteries can work. So this explains it in a visual. So you have your renewable sources, and they produce electricity, some that is going to be used directly to your buildings when you have demand for this power. But in some cases, not all the energy needs to be used at that moment. So they will use the excess energy that could be going to waste, and I'm going to store it in these sand batteries as heat. And then when the demand is greater, maybe the power being generated is not enough to fulfill the demand, you can draw energy from these batteries that has been stored and be able to meet the demand for your buildings all year round. And it's very beneficial in that way. So I'm going to get into now why this is important. So it's very clear that diving further into renewable energy will only be possible with scalable, affordable, and reliable energy storage. To me, there is a lot of research being done with energy storage, but personally, I think on-site thermal energy storage for buildings is largely overlooked, and I think there's a big importance for us to be looking into this more. So it does allow us to further depend on renewable energy and less on fossil fuels. It's also important to us who are following in the alternate energy pathway, as this allows us to dive further into our careers and expand our knowledge a little bit more on this topic. Our environment here in Canada, as you know, gets very cold in the winters, and we have a large demand for heat in those months. This battery can be an important part of meeting that demand and help out with the heating in our winter months. But not only for that reason, the battery is also very environmentally friendly on the way that it is built. And I can't not mention money. This is a great way that we are able to save money in the long run. Now, I wanted to talk a little bit about this figure right here. For those of you who took solar with Mr. Metcalf, we have discussed this, but for those of you who might not know what this is, it is a duck curve. So it compares the power generation throughout the day, and I wanted to talk a little bit about this because, as you can see, here's around 12 a.m. and your power demand is decreasing. As we're waking up around 6 a.m., 9 a.m., it starts to rise again when we want to shower. We're turning our lights back on. Now, throughout the middle of the day, this demand decreases. This is because we're at work, we're not at home using all of this energy, and then when we get home from work, it spikes up a lot. This is when we might be cooking supper, maybe you're doing laundry. So this spike is a big problem because the power plants need to be able to adjust to this accordingly throughout the day. But as you might know, solar actually produces the most amount of energy at this period of time when we don't really need it. This power here that's being produced by solar that we're not using directly is a great opportunity that we can store within these batteries to meet this rising demand in the duck curve. So now I just want to get into a little bit about how I built my battery. So this is a new technology, so there was not a lot of information that I could find so far on the build of these systems. I reached out to Polar Night Energy, but they unfortunately didn't get back to me with some tips on how they built their battery. So I got creative, and this is the design that I have come up with for my system. So I have a pull box here. It's a 16 by 16 by 8. And I have my copper tubing that runs through my battery, and a shut-off valve for the user to be able to control. I also have an oven element that I use for my heat. Picture this as the sun, and you're on a beach with hot sand. This is basically my sun within my battery, charging my sand. The container is also insulated and filled with sand, obviously. And I used just the wall outlet to simulate excess renewable energy, because for the scope of my project, this is the best way that I could just simulate this energy for my build. To get into a little bit of my thought process, I have my electrical receptacle going directly into my heating element. This is then inside my battery, where I have a temperature probe and inserted into my battery, and also one that is collecting the waters for the water. This data is recorded, and also time is a factor in my analysis, so that is included as well. This is then, I have some theory, so I have my question that I came up with for my analysis, my hypothesis, and this goes into my PCB, or my PC or laptop, where I have my Excel sheet, my analysis, and then that brings me here to my result presentation. So, I know it's kind of hard to see my battery as it's built, but I included some of these pictures so you could follow my process that I went along with. So, as I mentioned, I chose a pull box for my container, as I could punch out the holes that I was able to need for my 1/2-inch copper tubing. I used a wire, well, I cut my copper tubing and I used a wire clipper to crimp 90-degree elbows. I chose this pattern for my tubing because it allows me to get the most amount of surface area with the sand in my tubes as I could. And then I attached my shut-off valve at the end. I also have this battery insulated all throughout the inside. And then I would cover these pipes with my sand so that they are fully covered before I place my element onto my system. I drilled holes for the wires, and my system is grounded. When I had the lid on, I used the screws to ground my system. You can't see in that picture, but it is grounded. And then after that, I would cover my system completely with sand up into the cover. And there's a picture of the element that I used to have my resistive heat. So another big, well, the most important part of my battery is the sand itself that is within the battery. So I spent some time in the civil engineering department, and I was working with the teachers there in the lab to perform a sieve analysis on my sand. This was a really cool part of my project because we don't really look that much into this, and the teachers over there were really helpful for me. I started off by taking a sample of the sand that I was going to use for my project, and I had a number 4 sieve and a number 200 sieve. So I take my sample and I place it into my 2 sieves, and I shake it as hard as I could. If it passes through the number 4 sieve, this is considered to be sand and not gravel. And then if it passes through the number 200 sieve, this is considered to be mineral dust and something that is smaller than sand. So I was really happy with the results of this. It came out to be 96.8% sand and 3.2% mineral dust. This is very important because the property responsible for sand retaining its heat is its thermal conductivity. Pure sand itself has a relatively low thermal conductivity, but this is a good thing because it makes it a poor conductor of its heat. So it wants to retain or hold that heat within itself for a longer period of time. Compared to things with a higher thermal conductivity, it wants to transfer its heat as fast as it possibly can. So that is sort of my process that I chose to choose my sand. The battery in general, you can use different types of sand or sand-like materials, but this would be the most beneficial for the system. So how did I collect data for my analysis? So I use this tool that I have here. It's a 312C temperature probe from TPI. I can show you up close in my demonstration later, but I use this to measure the internal temperature of the battery, and also one of my main things was my change in temperature of my heat transfer fluid. So the heat transfer fluid that I chose to use in my project is water, and I was able to measure the inlet temperature and the outlet temperature of my water that I would be using in my system with this temperature probe. I wanted to talk a little bit about my test one, and I realized that accurate is not the correct word, and I should have used precision for this test. But I compared my probes to the amp probe thermometer, and as you can see in the picture, I was very happy with these results, that they were the same as what I was getting on my temperature probe. So that made me have some confidence in that my values were correct and backed up by this. My test number 2, I was unable to complete as it posed a safety risk, and it went against my safety risk assessment, as I was going to test the temperature limit on my battery, and I decided it was unsuitable for the labs here at NBCC, as it can get very dangerous. So maybe in a different environment, I'll be able to conduct that test. So after I get the data from my temperature sensors, or probes, I created this Excel sheet to organize my data. So I have all my formulas integrated into this sheet. As you can see here, I have it in formula view, but I'm going to show you some values during my demonstration. All you need to do is plug in the inlet of the water inlet temperature, which I kept at a constant 16.7 degrees for consistency through my data collection, and then you just insert the outlet temperature that comes out of the battery as well. So this sheet relies heavily on the MC delta T formula, where the mass is kept constant, and the mass of my sand is kept constant, and the specific heat of my sand is also kept constant. This allows me to get my heat energy output in joules for each case or cycle. And then I am able to get my capacity from the heat energy by dividing by 3,600, because 1 watt hour equals 3,600 joules. So that is how I'm able to get that. So this brings me to my analysis question. And my question for this project was, is this a storage solution an efficient way for storing renewable energy? Before I get to the answer of my question, I wanted to back up my answer on what I'm going to say. So the next couple slides are to be backing up my final answer to this analysis question. So this is something new to me, as I just kind of discovered this doing this project. So there are so many things that I had to consider and that I've learned for this process. I wanted to organize this in my own version of a data sheet for my battery. So I tried my best to replicate a data sheet for another battery. I understand that this is not your typical battery, so some of the terminology may not relate as greatly, but I wanted just to be able so you guys could compare and know these terms. So the capacity of my SAM battery came out to be 445 watt hours at 100% charged. At 3 hours, after 3 hours of storage, it came out to be 358 watt hours. After 6 hours of storage, it came out to be 287 watt hours. And at the capacity after 12 hours of storage, 103 watt hours. Now, to get in a little bit of the depth of discharge, as you know, for a normal battery, it stops you from utilizing all of the energy within the battery to protect the life cycle of the battery within the chemicals. But my battery is a little bit different, as you can harness 100% of the energy that has been stored within my battery. So that is why I provide 100% depth of discharge, and this also does not affect the life cycle, as every time I charge my system, it worked the same and is able to store the same values within it. The fluid holding capacity in my battery is 0.4 liters, which is around a cup and a half of water. My COP is 4.83, and I'm going to get into this a little bit later to discuss how I got that value. So it's just one battery per container. My battery weighs 80 pounds. The dimensions are 16 by 16 by 8 inches. And my insulation, R value for my battery is 3.7. Insulation is a key factor within this battery, as it helps the sand retain the heat inside the container. I would love to get this value a little bit higher in maybe some future process. Like if I had some more time, I would like to consider this. But I had to use fire blocking insulation for my battery because of the high temperature. So this insulation was the best that I could find for my application, and that is where that value comes from. So a little bit about charging my battery. At 100% charging, my temperature is 100 degrees, and this was controlled by myself and decided that this would be a good limit for my battery. The charging time is 30 minutes plus or minus 5 minutes, depending on the ambient air temperature of the room. The charging power is 2,400 watts, and the amps being drawn by my element is 4.75 amps. So a little bit about the storing cycle for my battery. I have discovered that my battery is able to store for a period of 24 hours. My graph looks linear, but in reality is not, but it averages around 3.35 degrees Celsius loss every hour for my system. I assume this is because of the small scale that I built, as well as the insulation. You can also have heat loss through the copper pipes as well leaving my system. So this is what I wanted to talk about. It's the COP or the coefficient of performance. This is what I use to essentially assess what my battery is capable of. So to find your COP of your system, you take your useful heat and you divide that by your input work of your system. So for my COP, I took the sum of the output energy that I could draw from my battery, and I divided this by the work, which is 2,400 watts for my element times 1,800 seconds, and that's how long I leave my battery plugged in for. And then I unplug it, so there is no more work being done by electrical after that. So after I do this calculation, I come up with a value of 4.83, and I was very happy with this because it is comparable to other systems, and I think for my build that is a pretty good COP value. Okay, so now this slide, I understand that efficiency is not the correct word or terminology I should use, but maybe you could explain to me a little bit what kind of word I should have used, but I will show my thought process behind what I thought over this. So I wanted to show you guys the heat transfer ability of my system. So I took my output water temperature and I divided that by my input water temperature. Here at the bottom, my numbers got cut off, but this is my 25th cycle. So after 25 cycles, it is above 150%, but I know that is not, maybe that's not the right word that I should use for that. I also wanted to do a little bit of comparison between my battery and Polar Energy's battery, just so you guys can see the scalability of this and what the potential is for this SAM battery. So the storing cycle for my battery, I found that it was 24 hours. The Polar Energy's battery can last up to hours to months. The capacity of my battery at 100% charged is 445 watt hours compared to the Polar Energy's battery, which is up to 20 gigawatt hours. And the temperature that I get my battery to is 100 degrees Celsius, where they're able to get theirs to 600 to 1,000 degrees Celsius. Obviously, it's a much bigger system, so they're allowed to do this. And I just want to say the point of phase change in sand is 1,700 degrees, so there is a little bit of buffer room there as well. So, in conclusion, yes, overall, I think this SAM battery is an efficient way of storing renewable energy, not only because of what I just mentioned there, but I also believe it's an affordable and sustainable and reliable way of storing energy. I think this also needs to be considered as is also big factors within these new technologies. Now, just quickly, how this technology can be implemented. District heating is a must for my technology. I can just show you a little bit. So you have your source that goes into a hub, which is then has insulated pipes going to where you want your heat. This is a map of Canada and all the district heating that we have here. It's not as implemented as cities like Finland, but we do have Moncton Airport is district heating, which I would love to see this implemented there. And I think it would be a great way for students here to also see that in that. So that is my end, and here are my references. And so because time is a big factor in my system. It doesn't have sound, so I'm going to just talk you guys throughout the video. Okay, so here I am in the lab with my system, and I'm going to plug my system in to simulate it receiving excess renewable energy from the grid. And this is, I tried my best to speed this up as fast as I could. It does gain some speed as we go, but I just wanted to show the system charging up to 100 degrees. And I should mention that these temperature probes that I selected were from -50 to 150 degrees Celsius. So it's just charging. Now, once it gets to 100 degrees, I am unplugging my system so that it can no longer power the element within the battery and stops it from drawing any electricity. So I unplug it and so here you can see my inlet temperature of my water, and I am going to put it through the system. I'm using the valve just to see when the water starts to flow out of my battery. I stop pouring my water. And then I'm collecting my water by opening the valve. And then you can see the temperature difference that I get. And I'm going to do another cycle here. This was performed a half an hour later than the first cycle. Okay, and I'm going to show you my my Excel sheet here, so that you can see as. Can you see that? Okay, so I can plug in my my water that I'm putting into my system, and I can change this value, say 51. This then gives me my output here, my heat energy in joules, and then my capacity here as 425 watt hours. So I know you guys can't see my battery from the back, but I just wanted to show this as well. So this is my lid, and you can see that it, one of my testing, I actually blew up my element, so that's why it's burned here. And this was at the initial part of it. And so you can see that my battery is full of sand. If I dig in here, you'll find the element and the copper tubing running through my system, and my wires going in, and that's my grounding wire as well. And yeah, there's my demonstration.
Yeah.
Okay, well, could you bring up the accurate versus precise slide?
Yeah.
Predicted that.
So you said, I'm gonna paraphrase.
I'm sorry.
So you said, and I'm kind of paraphrasing here, that this should have been a slide titled precision and not accuracy.
Yeah.
I beg to differ.
I know we had talked about this a lot, so I did some I think it's precision because I'm using two things to measure the same value. So I'm really measuring how precise they are to each other and not necessarily.
Let's just look at the term precision. What does the term precision mean?
So it's how close the measurements are together.
If you have a digital multimeter, what's set on volts?
Yeah.
What's its precision?
I think that would be stated like.
But if you look at it, you can even look at it and tell us what it's. You can look at it and say, hey, this is this.
Oh, like a tenth or.
There you go. It's the number of.
The units.
Right?
Yeah.
If you have a hard time remembering precision, think of resolution.
Okay.
Okay, precision and resolution go hand in hand. How accurate is it?
Okay.
Then you have to go look up.
Yeah.
Okay. So are you testing here for accuracy or precision?
I'm testing for accuracy.
Because what are you looking to find?
How reliable my temperature probes that I selected are. I'm trying to find
How close they are to?
another source.
That's right. How often do they give the correct answer or nearly correct answer?
Yeah.
So that's accurate. That's plus or minus something, right?
Okay.
Okay, so that's accuracy. So you're right. You're testing accuracy.
Okay. Oh yeah.
What's another way you could have done this besides another temperature sensor? Let's say you only had your temperature sensor. You didn't have the other one. What's another way of testing for accuracy?
Maybe having multiple things to measure.
Yeah. It wouldn't tell you though. It would tell you how close you are to a value, but you wouldn't really know that value, right?
Yeah.
What you're testing water, right?
Yeah.
Temperature of water.
Yeah.
What do you know about the temperature of water under certain conditions?
Changes phase.
Sure. So when it changes from liquid to solid, what temperature does that happen at?
100 degrees.
From liquid to solid?
Oh, like zero.
Zero,
Zero.
right? Exactly. At sea level and barometric pressure. Okay. So you know that's happening.
Yeah.
So if you had a container full of water and ice, and you mixed it all up, and you let it sit there for, I don't know, hour,
Okay.
what do you think the temperature of that water is with the mixture of ice and water?
So it would be really close to 0 degrees because
So if you stuck
because
a
of the
thermometer
ice.
in,
Yeah.
not against the ice, just near it,
Okay.
that ice water bath should be 0 degrees. So
Yeah.
then you can calibrate your sensor, say, oh, that's what 0 degrees is. Even though your sensor may tell you it's 1 degree Celsius, that doesn't matter.
Yeah.
If it tells you over and over it's 1 degree Celsius, well, you know that you're off by 1 degree. So,
Yeah.
what other condition could you measure for?
Well, when it's boiling or when it's vaporizing?
Sure, when it starts boiling, or it
Yeah.
starts, if you're near the surface, again, at sea level, barometric pressure and all of that,
Yeah.
you would be able to, again, read if it's 100 degrees Celsius.
Yeah, I think that might have been good too because it also can test like my limitations because I didn't want to have evaporation because I didn't want to get into that sort of thing. So maybe I should have.
So, but you could have
tested
calibrated
it as
your
well.
probes
Yeah.
for that, using that. There's nothing wrong with using an external device too, if you know that that's certified and has been calibrated.
Yeah,
I don't know if those have been, but
yeah,
it doesn't matter. I mean, it's giving you an idea what it is. Right?
yeah,
Okay.
yeah.
Okay, you talked about seed analysis,
Yeah.
and you said that's important. So what's the, should I say, what are the optimal values?
For my s-
What you said, like percentage of mineral dust
So, yeah, that's a good question. I was trying to get 100% pure sand. And that would be like the optimal value, like the thin, or not thin, a fine grained sand. So this was like really close to 100. And I honestly think that the mineral dust might have been from like me shaking and like the sand breaking down as well. So throughout research, it's if you can get like pure dry, dry is also important, sand that's like the optimal for my system.
Can you find it?
Yeah, I think you can find it if you were to go dig like outside or maybe not. I know the batteries that they're making right now, they're taking sand from construction sites that are going to waste, so they're able to reuse the sand. So, and I don't think that would be 100% like pure sand. So that's why when I was saying sand or sand-like materials, that's kind of what I was referring to there.
And what's the impact on the, let's say, the efficiency or whatever you call it of your battery?
Yeah. So,
What's COP exactly?
so that, it's the thermal conductivity basically. So the larger the sand gets, the higher it has. So it wants to like release its heat faster. Where the finer it comes, it's going to be able to store it within itself for a longer period of time. That's what I want for my system. So that's why this is best.
So which factor of sand is that? Which parameter?
Conductivity. The way it conducts heat.
Yeah, I think you're more looking for specific heat. Specific heat tells us how much energy it'll hold, right?
Well, specific heat also is like how much it takes to give it to the sand.
Okay.
Where I'm mostly focused on like how it would.
How long was, okay.
Yeah.
Okay.
Yeah. But that can affect that too, like the specific heat allows it, like how fast I could charge my system. But yeah.
Well, it would be how much energy you can put into it.
Yeah,
For the
exactly.
quantity of sand.
Yeah, for sure.
Could you bring up, you had your spec sheet, which I thought was an interesting way of doing things.
Yeah.
The only thing I don't know the answer. I'm gonna ask you a question, but I don't know the answer.
Yeah.
I have to look it up. Capacity in what hours? For me, electrical capacity is in amp hours.
Yeah.
So I'm asking you, is that the right term to use in a thermodynamic sense? Because this isn't electricity, right? We're talking about obviously thermal storage. So is the term capacity really the correct term there? Or are you just using it to analog to a regular battery? You know?
Yeah, so I also went through that thought process because I wasn't sure what I could do this, but I went off what the company in Finland is doing, and they're measuring their capacity at watt hours.
Okay.
So for me to compare the scales of my projects, I went with the same thing.
That's fine then. So you're trying to just use what they're, because
Yeah.
for me, capacity is an amp hour, which is an energy storage, but it's electrical energy, right? So
Yeah.
I was just not, I'm still not so sure it's maybe the proper term for it or not. But
Yeah.
that's why if you're using it from their aspect because you're one compared to them, I can look at that.
Yeah.
Okay, so,
Last one.
last one?
Yeah.
Can you go to your question slide?
Yeah.
Kind of a comment here. How did you answer this question?
I say yes, that overall I thought that it was,
Okay, good.
yeah.
What is your proof?
I proved that in here, I showed my slides here.
Just go back to the question and relate that to your proof.
COP is a measurement of, for geothermal and energy like storage systems. It's a way of proving that, because your COP can directly relate to your efficiency of your system.
Do you have other things to compare to reflect on? Because like this number, I don't know what this number is.
Okay, yeah. Mhm.
You said it was comparable, but you never gave examples.
Okay, yeah, so like a heat pump, for instance,
That's
it-
my comment. It's like we
Okay.
should have added something so we can,
okay, yeah.
thank you.
I think we should put it here.
But that's at an angle this way, so once you have to do it this way.
We didn't give her an answer, by the way.
And this one, I think.
I'm not sure what people want. It's sufficient.
Yeah.
I think I should try to turn it. Maybe. No, it's gonna fall. Maybe how strong this one. I think it's strong enough. But
Push that over.
but this one. Just put it on this enough because of the dry. Thank you, baby.
Pepper, let's work it for you. You can see it on the camera. You can see it on the camera perfectly.
Can you see it?
Yep.
Here, this way. It's against my concept drawing, because my concept drawing is like this.
You don't even remember what you
I'm going out of the room.
That's where my last slide is.
It's from the auto house. It's from the ocean. Yeah, that's all right. It's called the other people. Well, I'm good. Oh, you're here? Yeah. I'm good.
Jason, you know all we're going to do.
I had to laugh yesterday. I'm sitting there at home and got the cereal and like, and it's really bothering me. I'm like, what if I could come up? I was like, what if I could come up with something and change? I know, that's why I always like realize that's why I well, what if I decide things or what if I learned differently? And if I submit a last yeah, really kills me when you're going to do it when you're submit that more, and that's why maybe down we but I mean, I'll keep I do that because then I know that like, well, maybe it's that like but like now Did you figure out your drop?
Huh?
Did you figure out your drop?
Yeah. Yeah. Well, it's here right now. It's the same. Here, it will have more. One more wall from here.
That's what you had, yeah.
Here.
Interesting.
I think because I tested two different branch. Because the lab have this branch is one breaker and this branch is another breaker. I don't know what else connected to this branch. I don't know what is connected to this branch. So I tested this here and I tested here. I did it. It wasn't just the same places. So that's why it's not accurate.
The system really gets much better.
Yeah.
You did a good job with your connections. Like from light to light. You did a good job with your light to light connections.
Yeah, thank you. It took me the whole weekend to...
Yeah, it looks super good though.
Well, actually it was 2 weekends. The first weekend was this one, the second weekend was that one.
Yeah, wiring is time consuming.
Huh?
Wiring and touching it is super time consuming.
I'm used to do multiple wire. This is a Well, the efficient cable and wire. Cable is the one that still have multiple strands. This is a wire, just one thread. It's harder to work this way.
Yeah, 100%. But you're sticking the caps on it. Yeah. Yeah, wire's way better than cable. Cable's way better than wire. You know what I mean?
Yeah.
Like, multiple strands is much better than one big
Yes,
piece of
all these electrical installations here are wires.
Well, yeah, it's 120 volts, so everything should be just wires. But I use 600 volts.
I had solid wire and then I was having a band.
I use 600, yeah, I use 600 volt, 600 volt strands wire, 12 volt stuff is but it's only true here. But yeah. Turn it off. Good job. Kind of just plug it in, but we're turning. Yeah, you never make mistakes. You were right though, was right. You weren't wrong, don't second guess yourself. Yeah, you were basing your accuracy on the probe, right? Accuracy is how close you come to a target, how many times you hit the same time. Like say you have time, and you should just think with this way, you have a gun, you're shooting a target, the center of the target, you hit the center of the target, that's accuracy. How many times you hit the same point? So if you have a target and you're accurate here, but you hit over here, and you keep hitting over here, you're precise, but you're not accurate. That was another
No, I mean, at the beginning, like, I was like, following it, I was really sad.
Here's what I thought, it just so people
It was probably the longest presentation I've ever But he was.
It's the other way around. Very straightforward question. What's the derivative of fixed Q? Yeah, it's going to be like 3x squared, right? And I'll say, okay, 2x
Okay, Ashley?
Okay, so time for the next presentation. This is LED light retrofit with payback with Mr. Ever Trejo.
Good.
Go ahead.
Well, good morning, everyone. Welcome to this SPL presentation. Well, as mentioned, Mr. Salah, my name is Ever Trejo, and I'm gonna present you what the payback with payback. This project actually is about calculating how much time you're gonna get your investment back, your payback from the switching from traditional light to LEDs. So, well, the project is my advisor is Mr. Chair. Thank you for all the feedback that we have in here. Also, Mr. McGregor helped a lot, and Mr. Juha helps with some kind of my drawings. So let's get into it. Okay, well, we have the overview here. I have the introduction of it, project overview. I'm going to tell you what's the project about and the steps of what it's going. I'm going to give you the test that I did in the data collection for this project using my board here. And that analysis then at the end, how the time we can get payback depending on the investment too. Okay, the introduction first. This is an analysis project, of course, and one is to answer the question how much time it's going to take to our investment in LEDs changing from traditional lights, that's incandescent, fluorescent, or whatever it is, into LEDs. So for this one, I set up a test ring, I call it light ring here, that have simulate incandescent light here and LED light here, and the equivalent for fluorescent and the same for incandescent LEDs and the same for fluorescent. So for this one, I measure the voltage and the current for each setup to get the power consumption because that's raw data. And then this all information, I put it in a spreadsheet that was prepared to give in the calculating the money saving in power and the time payback. So here it goes with overview. Well, as mentioned before, I have the board ring here, and I have set here two set of digital power meters that have the capability to give me voltage and current in real time of this setup. And taking all this data, put it in the spreadsheet to get the power. Well, get the power because you formula is power by voltage, we're gonna get power. So we get the power consumption. So the spreadsheet we can give me the payback of the investment. And why I choose this one, because when we're in discussion with my advisor, we can do the project only in Excel and put whatever the manufacturer give us to get out payback in investment. But it's better have an idea in real time, in real life, what actually is happening there. And some surprises I found here. The lamps consume a little bit more than the other one, and other stuff, the other things that comes in the consuming of power. So enter this data, as mentioned before, in the spreadsheet. Estimate the usage of the home and settings of office or industrial also, and analyze these results in the spreadsheet, and of course enter the conclusion. Okay, let's go around with my block diagram here. Okay. Let's start here. So this is, how you can see, this is my light ring, it's here. And here is where the power monitor is gonna gather the information that I gather and to put it here in the spreadsheet. And use the estimate cost of maintenance of this light system that I'm simulating here, and also put it here in the spreadsheet. So it will give us a calculation of retrofit because we can have savings only in power, but have something else, that's the maintenance of the light system, and then report the conclusion. That's why I am here. One thing I want to mention, I'm using power monitor because the the rough idea at the beginning of the project with my advisors in the discussion of design was that we use a DAC for getting data, for get direct data, go directly to the computer. So don't human intervention have to be to have some errors and stuff. But sadly, the DAC has limited capabilities for getting information on voltage and current. I contacted the manufacturer and they told me that, and what else? I told them what I want to do with that, and they told me that the DAC won't last 1 minute with 100 volts and more than I think it was 5 amps, something like that. He told me that. I told them the scope of the project. He told me your DAC is not last. So I went to this program and it's still here. So we have this alternative, use the power monitors that we have in the lab. In this power monitor, have the capability to give me voltage and current. That was the primary idea of using the DAC, getting voltage and current to put everything here in a spreadsheet, and it can be calculated by itself. Well, this is the electrical diagram of my project. You can see here, this is the connection, the wiring and everything of the incandescent light ring, the electric rings, and fluorescent, and the straight lighting, that's the equivalent of this one, as well as the LED, the equivalent of the same thing. I here have my power monitor. I use the symbol of power monitor because that was the symbol of the actual power monitor, but I'm using it just to get the voltage and the current, to have rough data to calculate that. And I use a power strip for the 2 reasons. One, for protection of the system, and protection or current or whatever can happen, or for aesthetic use also. Our safety risks, if you see my project, I have plugs here. So these plugs cannot direct it with a base or have anything wired exposed to the outside for safety measures. And these 4 drive strips go to connect to a 5th one. That's the main source here. It's in the back. You cannot see it, but it's here in the back of the board. So, and then I come here. Well, this is my original concept. Was one of my first ideas when it came to measuring power, voltage and current. When the discussion was with the advisor, then I told him, if I simulate a lighthouse, a residence with maybe 3 lights, and versus LEDs, compared by one by side, and the same for fluorescent, can be office or can be industry, and also put actually in the beginning was the DAC going to getting the current that was connected to the power strip and then to the DAC, but it changed to power monitor. So this is the first idea that came in my mind. So I constructed is the board you're seeing here. So well, you see here 4 power meters. Actually, I just have access for 2 of the same brand of P3 International. I have a 3rd one here, but it's a different brand to make more data. Compare pairs to say that. That's why I stick with the 2 of the same brand in the same model. Okay, and now, well, I was telling you that this thing, you're saving power in changing from incandescent light to LEDs. I give a small example. You say that you have a 100 watts light bulbs and you're switching for a 20 watts LED, you're saving 80 watts, right? Well, this is an example. And you're saving that money, that's 80 watts in power. So you say, okay, I'm saving 80 watts and that's it. But also, these are the lights, incandescent and fluorescent, every light has a lifespan. And the lifespan of this incandescent is lower than the LEDs. And the same for fluorescent, for LEDs, they're lower. So I have to take in consideration that information too, because it's important that in the lifespan of your investment, you can save money also in replacing those lamps. And also, there's a labor cost in replacing those lamps that was involved in this one. Well, I'm gonna right now give you a small example lifespan of a bulbs and everything. So I want to apologize first for this one. The first one is I use this is more lamps if I use these 2,000 hours. This one is it's a brand, not new good brand, and I was doing testing and looking for brands that have not good. There's brands that have a dollar sign on the package that was warned for now the instructors here to avoid them. Thanks for the warning, because they're cheap and also they don't last like the brand one. So actually, this one is based on 5,000 hours using the most power we have. Philips 60 watts. According to the website instructions, because they don't send it here sadly. And this one is based on 5,000 hours of life cycles. So it gives me through 3.2 lamps you can change in the span of 5 years. In this 5 years, etc. But actually, if you use the real consumption of this one, there was like 3,000, you're going to have to change around 7 lamps in the span of 5 years. And for the LEDs, you have 15,000 hours to 10,000 to 50,000 hours. This is one of the best brands. In the 5 years, you're going to change only one. And that's where the maintenance comes. Now, comes into fluorescent. Fluorescent also have a very long lifetime, but not compared to the LEDs strips. So this one, it takes 10,000 hours lifespan. In 5 years, you're going to change maybe 2.87 yes lamps, maybe 2 lamps in a span of 2 years, depending on the usage. But using it 12 hours in 360 years per year. The same LCD, you can see here, this is 30,000. You're not even close to change 1 lamp in a span of 5 years, according to the specification. Also, in this part, I like to mention, because this one goes to the office of professional industry, you have to pay someone to replace those lamps. So that's labor cost, also extra cost of the lamp, and cost of the guy you pay to go replace those lamps when the lifespan goes on. That one information also goes to the spreadsheet to get the retro feedback. Well, now I'm going to go to the testing. The testing that I did to the power strip and LED equivalent. So the testing individual test I did was doing and I'm gonna close here. Individual test load by volt, and then this one was getting the current and the voltage for each one. So because they're in parallel, to get the total of the current of each light, you have to sum them because they're parallel, and get a mean for the voltage because the voltage and parallel is the same. So I run this test in the incandescent LEDs. You can see here, like at point, you can see the difference of amps that they consume here, and I run it also in the fluorescent lights. Even in this one, there are 2 lamps, remember? Usually all of them, in the office they use 2 lamps because it's recommended for the visual aids and things like that. But I didn't do it in the power strip because this one is one fixture. Now they sell all the LEDs comes in one fixture. They use 2 strips or maybe just one with a reflector, or maybe there are 3 inside, they use a reflector too. So at the end, everything comes on one strip. So this one was not necessary to do that individual light bulb test. Okay, and then And then I did what I did to test also my power monitors. I tested against the Fluke 350. I believe it's the one that is sold here in the college. Doing a multimeter test because I'm measuring current and voltage. So I use it as base at the Fluke multimeter because it's more, or for us here the technology is our brand. Us base are more reliable that we have, that everybody say, hey, you use the flock. Because in doing this test, it should be done in a lab with temperature controlled using special devices to have more accurate one. But for me, for this project, I just use the flock as a base one to have the accuracy. I have controversy right now with that one, but I'm gonna stick with accuracy of my meters. So at the end, taking all the means of all the tests that I did, I got that it's 98% of the accuracy that we have in the light system. So, and here is the data collection. The data collection that was run, each ring was run for 5 hours. So each hour going collect what the meter was given to me. So I got this one, and this information here, okay, this one here at the end, this one and this one goes to, it was placed in a spec sheet. Well, I gathered this manually and then put it in the spreadsheet. This one goes connected directly to my spreadsheet to give it the calculus of the voltage and the current of each system that's going to be in results, and I'm going to show you them in the demonstration in the spreadsheet that give me the time. And also here right now I'm going to go to show you an example of analysis of this analysis, because I'm going to show you one example with the main one. Because if I go all through the formulas explaining how I get the information for each one, it's going to take me longer than 30 minutes just to try to give example to get to the final point. Okay, and this one I'm going to give you, and this is another example, I'm going to give you an idea how to get here for this information. This is an example, actually. Well, if I had an initial cost of $4,044, initial cost of LEDs replacement of my new project, and the initial cost here because is zero, because our all system once it's connected to the building, it start working in the box, it becomes zero. Because at that time it's going to be money for us as a consumer. It's no longer valuable. Well, it's valuable, but because the investment now is gone. And then the annual the annual average operation cost saving. This is what I was to get to. To get here to this one, the annual average operation cost saving, it depends on the hours. We're talking about the hours of a lifespan of the light bulbs, right? And we talk about the maintenance cost to pay the guy who changed that, right? So to get this one, first I have to get the annual average operation cost of the actual system. How this one? Just multiply the hours of usage of my office, for example. Remember the 12 hours multiplied by the usage day. And that one, I divide it in the lifespan of the lamp. That one, I'm going to replace it. And that one, that is going to give me the quantity of lamps in 1 year. I'm going to have to change. And then I multiply that, the cost, the sum of the cost of each lamp plus the cost it's going to take time to replace the labor cost. The labor cost is based on how much time it's going to take the technician or the labor person who said. It's going to much time it's going to take. You're going to have to put that in a spreadsheet. Times you're going to take in how much you pay for hour to it. So that cost goes plus with the cost of the lamp, and then we multiply that one with the cost, the number of lamps. And after that, we add the cost of the consumption of the actual power. That's going to give me how much I'm paying on only in power, also in maintenance in 1 year in the lights, in the actual lights. And then I go against my savings in LEDs. So this one, the actual cost of operation minus the saving and the operation of the LEDs. How the LED is going to be saving me against this one. So it's gonna give me the annual average operation cost saving. That's what I'm gonna save for switching in LED lights. Now the whole scope, the whole thing means maintenance and power saving. Not only power saving, this is maintenance and power saving. And this is gonna give you, for this example, it gave me $467 per year. So I divide this and this one with this one, and it's gonna give me three years, and I'm gonna get my payback in that investment. Okay. So, and so you can see here, this is the scope of, I hope that I was explaining well, but I'm gonna tell you, this light says switching to LEDs is not only to save money in your bill, because you're gonna save money also in buying more lamps in the future. You're gonna save you money to pay someone to change or replace that lamps, and that scope usually nobody else see it. So adding this one is gonna take me to that number. Well, now I'm going back, going to my conclusion of this presentation. So retrofit incandescent fluorescent light LEDs reduce power consumption, as I was mentioned before. This is a good thing because always the bill of us is saved, but also we're saving power to or MVP power. They can say that it's not gonna give, and it's not gonna use more fuel power to give us to us, because we are reducing our consumption. Save money in maintenance system, as I mentioned before, because the lifespan of LEDs is triple. It depends on the brand, it depends on the type. That's why the spreadsheet has all this, all this data you can put there depending on that, and you can have your retro feedback. And the power savings, for example, for my grid here, is going to be paid if I connected in dual the lifespan. It's going to be it's going to pay itself by half in a year, and the incandescent, and it's going to pay the fluorescent one in 1 year and third maybe, if I use it all as and this one. This isn't only an example, so to have an idea. So there's very benefit of this this payback is a lot of benefit. Yes, light is feasible. Changing to light is feasible, and also I got the spreadsheet that was giving me the time for that payback. That was the important scope of this project, and the savings that I have per year in each store. The spreadsheet that I have is not perfect. I know that it needs to be more. It needs more, definitely, because about half the basic scope that we're looking for is the year saving and the time that they pay back. It's not precise. It's an estimate that I'm getting in here. It's not precise information, of course, but it's going to give you an idea how much time you're going to save and how much money you're going to save per year, and the time of the retro feedback. Well, and also I like to mention thanks to my advisors that helped me in this project for going back and forward and all the information that we have a lot, and all the instructors for all the information that give us and give ideas to get this project. Also my classmates, thanks for all your help and for your time in this one. And also I'd like to thank to my mom, because she was the one inspiration to get here. I'm not getting emotional, okay? No. Because she wasn't for her, I won't be here with you nice people presenting this project here in NBCC. So I'm gonna move them to my presentation, my function presentation. Well, just to wrap it up, yes, it's feasible. Yes, I can answer how much time I'm going to take in my project. Yes, I can do it. And also, that one question that wasn't in this project is how much I'm going to save in per year. But the spreadsheet was hard to get into it, and it's going to give me that answer. that I was looking for. So that's it, and I go to my okay, does anyone else is here sensitive to the lights? Because this is gonna get very bright right now. That's no problem? Okay. Well, okay, this is my presentation. Okay. Now I go to my, okay, go to the spreadsheet and I'll go to the camera. Okay, perfect. So, for my demonstration, I have my spreadsheet here, and I'm gonna, if you can see it, maybe good now. That's too bright. Okay, here in my, well, here I'm gonna get up from the camera. Here's where I get information of the days of use in the house, the days of the, and all these ones are estimated or calculated. It depends. When you're showing this one to a client or someone you want to sell this one, you have to put the rates that you have on it. I use this one estimating the uses in the house and power that we consume right now, the money with it, NB power. So, and then all this information here in the actual, you can see here the actual test, and lightning test is where all information comes from the test that I did, the data that I collect. This one goes to the spreadsheet here, and it goes do all the calculations and give me here the retro feedback of my project. Right now, I'm gonna turn on this one. Maybe if I can move the camera here. Okay. Well, in my power monitor, let's try. I don't know if you can see it because it's too bright. I think it's difficult to see. Well, I got here for my voltage and LEDs. Well, you can see here. You can, okay, this is measuring voltage. Sadly, I cannot go that longer. But you have an idea what information that I get here from my light set to my spreadsheet. So I saw, let me do this for the LEDs. I had 19.5 volts. Okay, 19.5 volts. Now go to the current. 0.34. Okay. 0.34. Now I go with the incandescent one. I have it's fluctuating 118.7. With a power current of 1.551. So, putting that information right here is going to give me that my power, if I my project with this information that I got right now, is going to be self-payback in 2.36 years. It's different, totally different than what I found there in the let me see here. Yeah, this one is good. Yeah. This is what I got. This one. This is the data that I'm getting for. I tested this in this spreadsheet. I was doing the calculus, and it is giving me. Here we go. So here we go. Because so we can see here, my spreadsheet is giving me that in my ring I'm gonna. Okay. 2 years, well, you can see 2 years, 2.36 years, it's going to be save money in this one, in the maintenance. If the project is bigger, it's going to stay the same rate because it depends on the money. Well, it goes bigger, you can see that. If we update the number of nights, we're going to, and we're going to give me this, okay, come on, I'm going to do this trick, maybe this works. Okay, yeah, it's the camera, definitely. Here we go. There you go. Well, and you can see that, here you can see the difference. Here's the 35 years. Maybe I got something wrong here. It's too much. Oh, maybe because I put in the cost of fixtures, 1,000, maybe. I don't know, let's say 35 years. It's too big. Maybe I go, what, 3? Okay, here we go. Well, I think it's too much. There's something wrong here because this saving was close to this one. Maybe if I go to this one, the lifespan of 3,000. Nope. Watts per fixture. Okay, this is my problem. This is too high. Yeah, this is a typo, sorry. Yeah, I got this wrong here. This is one, this amps is divided by 3.
Okay, Heather, that's enough time to...
Yeah, sorry for that. This one is divided by 3.
It's time to go to the Q&A.
Okay, go ahead.
Yeah.
Go ahead.
Okay, I see that you compared incandescent and LEDs. How about halogen?
Halogen, that's a really good question. I didn't consider doing that because I went to the most common user, that's incandescent and fluorescent. But that's a good point. Maybe try halogen. That's the one they use in the street, right? In different lighting. Yeah, you're right. No, I didn't consider that. But that was a good, interesting point in that. Maybe for future projects, we can put that to also get that one into it. Because it's a really good question. Now, anyone else?
So, from what I understood, your basic premise is really just comparing energy consumption.
Yeah.
One thing that I would be interested to know, whether you consider that is, you know, all of these lights don't necessarily light up the same amount.
Yeah.
So I would like to maybe have seen a normalization of those prices based on, you know, light intensity or whatever factor.
Oh, yeah. I didn't consider that factor.
Because that is something else, right? You know, like when you change lighting style or lighting technology,
Okay.
you want to replace it with technology that is the same, if not better, depending. I put better in quotes, depending on what you want, right? So
Yeah.
did you consider that, or?
No, I didn't consider that. Yeah, definitely, because I just was going to the whole scope of office or a house. I didn't go to very detailed. That's a very.
Because
It's
the
like,
number of lighting units is going to be different, right? For a given room for the same amount of lighting.
oh,
So
you're right.
then that affects all your return on investment. You know,
Yes, and
on that, right?
yeah, you're right.
How many bulbs do you need for incandescent bulbs versus LED versus?
Yeah, it can be a difference between them. Yeah, but I didn't consider that too.
For your power monitors, you kept mentioning that it measures voltage and current. What does it measure? What does it do?
Well, make sure the voltage is going directly in the
Does it
level.
measure just voltage and current?
Well, these power monitors, they monitor.
You turn the camera off.
Okay, sorry. Yeah, it's making.
Oh, it's fine if it's
Okay.
not.
Well, the power monitor, yes, they can do a lot of things, but I don't take in consideration the others because they give you volt amperes, I believe. It give you frequencies, also give you the wattage hour of use in the between time. I contact PA3 to ask them how it measures the power consumption. They only send me back a video of how they use it, but then actually they don't give me the science, what's behind the power monitor. I was doing the research and only I find out the guys that assemble this thing and show the ICs, all the external stuff, but they don't explain actually how it works. So that's why I just, like was in the beginning of the project, just taking the voltage and the current. That was the main idea at the beginning of the project to do with the DAC.
It's called the power monitor, does it measure power?
Yeah, it measure power, but yes, it measure power. I can do that, but it's like going can tell, well, ¿cómo se dice brincar en inglés? En one Spanish? Jumps, a very important step that I was in the beginning of the main idea of the project, use the voltage and the rough data, the voltage and the current. Yes, it used power, but I decided to put that away because I was better going to rough data. Because, oh, by the way, I don't, I don't know if I can measure power consumption. When I'm doing the testing, I don't have another way to, if I use the power consumption of the meter, I need to get another power meter that was reliable to make comparisons to do the testing. So the only testing that I did was against a multimeter. That's why it goes all the way now, voltage and current.
Oh, yes. So you said the DAC could not,
No,
so what was the limitation?
70 volts.
Oh, it was a voltage limit.
Yeah,
Okay.
yeah. I showed his the year the email
So it was a
manufacturer. Yeah, say it won't last a minute, right?
Yeah.
Yeah, it won't last a minute. It
Oh,
won't
see, that's how it works. Yeah, probably for more than a minute.
Well, that's the answer we get from the manufacturer. Yes, it won't last a minute.
And it won't work after that minute ever.
Yeah, yeah, and they're gonna shine me that, so okay, go.
Yeah,
No, no.
yeah.
So your conclusion was what in the end? I was a little.
The conclusion at the end, yes, well, one of the two of conclusion actually, is it's feasible to change to LED lights, and also that I got my calculator for the payback, that was my spreadsheet, that when I get all the information that I put it there, what the project's gonna be, I'm gonna try to switch back. Sorry for if the light's gonna bother you. So the second important thing about it, well, the first thing is the payback time. They're gonna get this one. If I get all the information.
So did you have that in your presentation? Why didn't you show that like as a graph comparing it?
Okay, the graph, yes, I was trying to do a graph trying to mimic what Red Screen does for the power saving, but I figured out the math after the project, after the
No, but I don't think you had to do anything as elaborate as that. I think all you had to do was take your numbers, obviously your return on investment numbers, or and just show which one was shortest compared to the longest. Or because you have a lot of data there, you may want to bring some up again. And to be honest, you explained it well, but for me, it was just these numbers that I could barely track.
Yes, I was trying to get that graph.
Your presentation here really is to show the conclusion of what you found in your report, right?
Yeah.
So,
Yeah.
numbers, numbers projected on a screen it's all right to show how you got something, but to get the overall big picture is not
I was trying to get that graph because the one that said the savings as it was negative. Then
well, I don't think you need that. All you really needed is you had 4 technologies, you had 4 bars showing which one's the shortest, which one's the longest, and this is the one that works. That's the shortest, so it's the better result. That's really all you needed, right?
Yeah.
I mean, in my opinion.
Yeah, you're right. So so the client can have a better picture.
Well, to have a picture, that's what I'm saying, right?
Yeah.
We're very visual, we
have
graphs.
Okay.
You ready? I was just gonna say bring up the Testing. Ask your question. Bring up your testing results.
The testing,
Tables there, yeah.
okay.
Not that one.
The 5?
Yeah.
The 5 hours? Okay.
Yeah.
Okay.
So did you do this test only once?
Okay, no, 2. Well, I did it, I have, I did another run test, but for display here, just put this one here.
Okay. So you did it more than once? You
Yeah.
showed
Yeah.
the results of one? Okay.
Okay.
Sorry, I just want to point out, if this had been shown as a graph, you could have shown all your results with an average value, and it would have been very obvious and observable. And, you know.
Yeah.
So putting up pages and slides of numbers, it's good to just kind of show maybe one of these, just to show what you were looking for. But then I definitely, in fact, you're telling us you didn't show all of it because you didn't want to have more. Well, that's what a graph is for,
Okay.
right?
Yeah.
You could put all those parameters down on a graph, and it would have been very, very nice and very
Yeah.
comparable.
Sorry for that. About my mind.
You got to think of who your audience is, but also think of what you're going to expose them to, right?
Yes.
Did you take into account the price of the box?
Yes. Yes.
I couldn't see
Yes. Yes, on the spreadsheet. Yeah, you put the price of the fixture, the replacement, the light bulbs, and both of the LEDs and the traditional ones.
You said there were some surprises.
Oh yes, the surprise that I found was in the fluorescent.
Yeah?
Fluorescent, because there's 2 lamps of 34 watts. When you go to buy a lamp, you say, oh, I'm gonna have 34 watts of consumption. But then after doing the information, I finally get 64 watts of consumption, because I believe it's in the banister that's consuming that power, and you're not showing it. Yeah, that's the rough data that I got. That's my surprise.
Your end results, you obviously had some theory behind, like reference, like when you buy a bulb, they would say like how much you could save.
Yeah.
Were your results close to that?
Well, no. Well, this one, well,
I mean,
it's better.
Like your results were better than the.
Yeah, the better you expect it when you see the savings on the, it's better, because the rough data is actually telling the people, oh, you're wasting more money in this one.
Thanks.
Okay.
With your data here, as you progress in your testing, the power reading, the watts is increasing for some of the tables. Why is that?
Maybe if, for example, maybe the incandescent one, because it's a resistor, burn, maybe consumption. Well, I don't know. I don't really have to answer this one, because I really we investigate that one, because.
Well, if an incandescent bulb is on for a long period of time, what happens to the
Gets
bulbs?
warmer.
It gets warmer.
Yeah, I burned one of them, by the way, doing the
And
data
you
collection.
mentioned the bulb itself is a resistor, so what happens to the resistor as it warms up?
Nah, it gets hotter. Oh, what
It does
happens?
get hotter,
Oh,
yeah.
what happens? Consumes more power,
Why?
because it's, I don't know.
For a resistor in itself, what happens to a resistor when it warms up? What happens to the resistance level?
Oh, the resistance level. But actually, let me try to go back to the electronic class.
Go back to year 1.
Yeah, trying to remember one. Yeah. The resistance level, if they get warmer. Electrons more. Have more flow of electrons. Lose the resistance.
You lose resistance?
Yeah, I'm trying to guess. I don't remember it. I mean,
The opposite
no,
of that.
it's the opposite, yeah. Now that I remember, yes, the resistance get higher, 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 yeah. Yes.
Right, it's minimal, but.
And that's why we have more power consumption, because it's a resistance. Yeah.
Thank you. Time's up.
Okay,
All right.
thank you for your time.
So welcome back to the afternoon's presentations, and we'll start with Marian, right? April?
Yeah.
Okay. That's for a portable Geiger counter,
Yeah.
right? And go.
So good afternoon, everybody. This afternoon, I will take you to the world of radiation detection, specifically the versatile and compact device called portable Geiger counter. My name is Marian Siringan, and I'm an electronics engineering technology student taking up industrial pathway. And the title of my project is Portable Geiger Counter, which I have been working for the past 5 months with the supervision of my advisor, Mr. Dennis Metcalf. So for today's presentation, here's an overview of my presentation for today. A bit of introduction of what a Geiger counter is, and then next, we'll go to the principle of operation, the sensing element of the device, and then we'll move to the concept drawing for you to have an idea of what my product will look like, and then we'll go deeper into the block diagram and dig into the schematic diagram. And I will also like to show you how I designed my PCB from my prototyping to the actual PCB. And finally, I will show you the testing and the results that I did when I finished the product, and then finally I will also tell you about all conclusions of this project. So for the introduction, what is a Geiger counter? So I chose this project because honestly, when I ran into this project, I don't know what a Geiger counter really is. I only know that it has something to do with radiation, but I don't know what it does and how it do it. So because of my curiosity, I read the article about this device, and then to tell you, Mr. Metcalf also gave me the magazine Nuts and Bolts where I based this project. So Geiger counter, or also known as Geiger-Müller counter, is first developed by Hans Wilhelm Geiger and Walter Muller in 1928. So the name Geiger-Müller counter was named after the developer. So why it's only called Geiger counter? Because initially Hans Geiger developed and improved the version of gas-filled radiation detector known as the Geiger-Marsden detector. So this detector consists of a gas, usually a neon gas, to detect radiation. And then Muller teamed with Wilhelm Geiger and introduced the significant advancement by adding a thin wire of electrodes in the tube for it to develop the radiation detection. So what does the Geiger counter? So I've been introducing what a Geiger counter, but I haven't talked about what it does. So Geiger counter detects and measures ionizing radiation. So ionizing radiation are the subatomic particles or electromagnetic waves in our surroundings, that have sufficient energy to ionize or break down the molecules or atomic of a gas. So yeah, and then for few applications of Geiger counter, it is used to monitor ionizing radiation in nuclear power plants, research facilities, hospitals, and other industries like for like security personnel, like that. And then it also monitors radiation in food contamination and other consumer products. It is also used by miners to test the ionizing radiation in radioactive minerals and materials. So to mention, Geiger counter also became popular during the World War II due to its ability to detect radiation. So during that time, nuclear weapons are a thing. So people seek ways to monitor this radiation through Geiger counters. So they're looking for ways to monitor the radiation by Geiger counter. So yeah, that's my introduction. And then we'll move forward to the principle of operation. So the Geiger counter works with a sensing element called Geiger-Müller tube. Geiger-Müller tube is like a tube that consists of an electrode. So this is the anode. The anode is like the anode is positively charged, and then this thin wall here is the cathode, which is negatively charged. So there is a neon gases inside the tube here, and then the mica window where the radiation particle enters, and it can also enter here. But this one, I think it's for the alpha because it can easily penetrate to a thin wall. And then when radiation particle hits this tube, so this is positively charged and this is negatively charged. So it has molecules here. So when this ionizing radiation hits this one, the particles here, the gases here, it will remove an electron from the molecules of the gas. Therefore, the electron will be attracted to the positive particles of this anode, and then thus creating a current pulse in order to sense the radiation particle. So here, the Geiger-Müller tube, what is special about it is that it requires a high voltage for it to detect. So for my GM tube or the Geiger-Müller tube, I use the LMD712 GM tube, which requires an operating voltage of 500 volts, but it could also operate at 450 volts to 650 volts. So it could detect alpha, beta, gamma, and yeah, that's the three particles that it can. So the ionizing, just to mention, the ionizing radiation particles that we know are the X-rays, alpha, beta, and gamma. So we'll move forward to my concept drawing. So this is an overview of what my device look like. So here's the front, and this is bottom, and this is the left side of my device. So at the front panel, you can see the sensitivity or the knob, potentiometer knob, which would adjust the voltage going to my GM tube. And then I also have here the power switch and power indicator LED, which is color green, for it to indicate the power is on. And then I also have here my alarm. For my audible alarm, I use buzzer, and for my visual alarm, I use red LED. And then at the bottom, I also have at the back of my enclosure, I have a 9-volt battery door where I can access my 9-volt battery that powers up my device. And at the left side, this is a hollow. So I drilled this one for the particle to enter the Geiger-Müller tube. So here is my Geiger inside the enclosure. So yeah. And then we'll move to my block diagram. So my block diagram consists of 2 major blocks. So this is my power supply, and this is my main circuit. So for my power supply, my device will be powered by a 9-volt battery, and then I have a control switch to allow a current to pass through my device, and it will supply a 9-volt to my circuit. And I also have a power light indicator which indicates the status of my circuit, whether it's on or off. So this 9-volt, when the power control is turned on, the 9-volt battery will supply my high voltage generator, my pulse detector, my current to voltage pulse converter, and my pulse width stretcher circuit. So for my voltage generator, when the 9-volt battery, when the power control allows 9-volt the current to pass through this, so the 9-volt battery will supply this high voltage generator, and the sensitivity knob will control how much voltage it would supply my Geiger-Müller tube. So here, the high voltage generator will generate a high voltage supply depending on the sensitivity knob, which will set the high voltage supply. So my range is 450, but in my device I'm using 500 volts because it is the operating voltage of my GM tube. And then once the GM tube has this operating voltage, it will now sense any ionizing radiation particle. So when a particle hits my Geiger-Müller tube, a pulse detector circuit will detect this pulse, and the pulse will, in order for us to process it for an alarm, it has to go to a current to voltage pulse converter and a pulse width stretcher. So these circuits are all powered by a 9-volt battery. So yeah, so for my pulse detector, since the GM tube is too small, it detects a radiation particle, and the current pulse that it produces is too small, and the pulse width stretcher needed a voltage for it to work. So I have to convert current pulse into voltage pulse. So this is the screen captures that I got last Friday. So this was taken after my Geiger-Müller tube. So this is the current pulse that I got from my Geiger-Müller tube. So if you see here, this is like too short for the alarm. So it just goes quickly. So it needed a pulse stretcher for it to to be detectable. And then here's the output waveform from the pulse width stretcher. So here's the output, this one. This is the normal condition. And then this is the pulse that I got during testing. And then let's go to my schematic diagram. So here's my schematic diagram. I have here my power supply. I have here a 555 timer. And I have here my 556 timer, which is a dual 555 timer. And I have here my my gem tube. So this is my power supply. So a 9-volt battery will supply. So the power switch will control the flow of current. And so here is the VCC where the 9-volt where the current would go to the circuit. And then this is my, I use green LED for status of my circuit, and then this is my current limiting resistor. So in order for me to produce a high voltage through my GM tube, I use a DC to DC voltage booster. So in order for DC booster to work, it needs an oscillator that goes high and low. That switch on and off for it to boost the voltage. So here I use a 555 as a stable circuit, but then I did not use the conventional stable configuration for this. So here the Q1, when Q1 reach a certain preset value of current, it will reset the 555 timer, which will then output here a current. It will output high, and then it will flow current here, and then the C2 will begin to discharge. So my on. So this is the overall circuit. So here it comes. Here is the current that comes from I, and then it will like dictate the on time of my 555, and then this RC network here will dictate the off time. So the on and off will go to the switch of my BJT. So here is a simple DC to DC circuit. So here is the pulse where we got from our 555, and then this BJT will act like a switch. So what it does is that when it is turned off, when it is turned on, VCC will supply current here, and it goes loop like that. So the voltage here will build up in the magnetic field of my inductor. So when the switch here turns off, it will flow, current will flow here. So the voltage that comes from VCC and the voltage build up here will add up, and we'll get a high voltage here. So yeah, so during the on state of this, this C1 supplies the voltage to this circuit. Yeah. And then after that, it will go through the 10 mega ohm resistor before going into the Geiger-Müller tube. So these values are required by my Geiger-Müller tube. So this 5 picofarad was the requirement for my GM tube is 4.7, but then I use 5 picofarad because of availability. So this capacitor here, what it does is when it quenches, when the ionizing radiation enters the tube, it will like voltage will come out here, and it will also like the GM tube will also have an avalanche of electrons. So this capacitor helps the GM tube to quench the avalanche. And then here at the cathode of my GM tube is 200K resistor that will protect the preceding circuit. So this resistor here will provide current here for the switch. And then here, when the BJT turns, and when it doesn't senses, it stays on. This one stays open. So the trigger here pulls this, the VCC pulls this trigger, so the initial condition of my monostable is high. So when this is closed, it will be triggered, and it will produce an output of low. And then after, this is the pulse stretcher circuit. So after that, it goes through a stable circuit again to process the alarm for LED and the buzzer. So let's move to my PCB design. So before moving forward to my actual PCB, I'd like to introduce to you my deadbug prototype, which was introduced by Mr. Metcalf during my prototyping. Because I have a circuit that requires a high voltage, I cannot use the standard breadboard which we use in the lab for my high voltage. So this deadbug prototype is like a electronic strategy that we use in prototyping, that directly connects the wire of the components together. And yeah, it looks like this. But after that, this is my actual PCB, thanks to Mr. Ligier. Yeah, and yeah, as you can see, this is my high voltage. So high voltage, for my high voltage, I use a specific spacing for it to prevent arcing. For my traces here, I use 40 mils, and for my pad trace, for my pad I use 120 mils, but for my IC, I use 100 mils. So I use mostly the bottom layer because of advice of my advisor, and only use three jumpers here because I have no way to connect it at the bottom. So here I connected my battery and my switch, and this is for the LED, and this for LED and buzzer, and this is for my potentiometer. And I also put a high voltage here for safety purposes in case someone will service this. So for my PCB design consideration, I use IPC221B, which is the standard for PCB design. So this is the formula that I use, and this, since I'm working with maximum 650 volts, this is the spacing that I need. So I apply that when I work on my PCB. So let's move forward to my testing and results. So the radioactive material that I use in my testing is this one. It is an uranium ore, which has a low level of alpha, gamma, and beta. So for my testing, I use proximity test to test the sensitivity of my device. So, and the expected result would be to count the radiation particle as it moves near the device, it should increase. So from the testing that I did, I have here the radiation. I have here the background radiation. So I tested it 10 times. So this is the total, and I divided by the number times I got the test, and the background radiation that I got is 19.4. So here's the graph for my result. And then for this one, I use the test 1 to test 5, and I have here different distances for my test card. And then I have here the average. So take note that 19.6, this average, you have to subtract what you got in your background test from this in order to get the accurate radiation count for the test card. So here's the graph for that. Unfortunately, I was not able to finish my battery life test, but battery life test is performed to prove the duration of device battery supply and power to count during its operation. So it will depend on the battery type, the frequency of use, and the conditions. So I got this in the one duration of my testing. So after 10 hours, I checked the voltage, and it's 7.72. That's the only result that I have for this testing. But the minimum voltage level for it to detect using my power supply is 4 volts. So for my conclusions, I would say that the project was successful. I was able to produce an alarm for my Geiger counter, which would alarm the user whenever they use it. And then for future considerations, I also like to incorporate a rechargeable battery for this project, and use a microcontroller and LCD to show the actual count of my device. And I also like to thank my project advisor, Mr. Dennis Metcalf, for helping me through this process, because dealing with high voltage is not easy, and he made sure that I was safe during this time of doing this project. And I also like to thank my friends and my classmates for giving me some insights and feedbacks in finishing this project. So that's all. These are my So, for my demonstration, this is my device. So I have here the alarm and the switch. So when you turn on, this will this will turn on to know that the power that the device is working, and then this is my sensitivity knob, and then this is my alarm. So what you hear now is the background radiation. So I have here the sample that I use in my testing. So when you put it near the GM tube, it like the thing goes faster. And I also have here another radioactive material which is used in smoke detector, which is the americium. So this is So as you notice. That's for my demonstration.
It would just be a word of what we're seeing.
Questions? Oh, okay. Do you want to ask her that question? Start with the schematic, I guess? Yeah, it's a good place to start. The draw test on the mouse. Yeah. Does it still work? Maybe zoom into the L1. Let's go look at L1. How about that? Is that your question?
Well, I was going to ask.
Yeah, L1. Yeah. I'll quote what you said. You said that the voltage will build up in the inductor. Okay, L1. Can you explain at what point, if the voltage builds up in the inductor, at what point that happens?
At what point does the we have a property of the inductor that when here the voltage will the current will flow here.
The pointer.
Yeah, use your laser pointer there. Yeah. Your on-screen laser, yeah, there you go.
Okay. So when the current flow here The inductor has a property to build up a voltage through its magnetic field. Am I in the right direction?
Well, that's what I was hoping you'd tell me.
So,
Yeah.
basically, what does an inductor try to do in any circuit?
In any circuit,
In any circuit, an inductor, what does it try to do?
it adds impedance.
Yes, but what does it try to do current-wise?
Current-wise, it reduces the current.
Not always, no.
It will like drive the. It will like drive the current.
Again, not always, no. Assuming I know what you mean by drive. An inductor, what does it do? If you have an inductor and you have current flowing through it, and also you change that current.
It tries to oppose the current direction
How?
Not the
by
current.
Mm.
maintaining the
Not the direction.
the voltage direction.
Well, maybe it's trying to prevent the current from changing.
Yeah.
Yeah.
So it does that by creating a voltage. How does it create the voltage across it? Where does it get the energy for that?
From its magnetic field.
And where does that energy all of a sudden appear?
Because of the switching of the BJT.
Okay.
So once when this is turned off, it builds up here, and then when it turns on, it collapses. The voltage will.
It's rate of change,
Yeah.
right? So whenever the current changes, so when your transistor turns on or
Yeah.
off,
Yeah,
what does it try to do? It tries to maintain the current.
It tries.
It tries
Yeah.
to, but it can't, right? Because the transistor opens.
Mhm.
Or if it closes, it runs out of energy in its fields, right? So what's the result of that?
When it closes.
Yeah.
When it closes.
Well, when it closes, it opens. What does it do after that? How does that turn into high voltage?
By because of the current here, because the current will flow here, so as it flows here, it will increase the voltage.
Not really. If I have an inductor and I put a DC voltage
Yeah.
across it, okay, does it do anything to the magnetic field of the inductor?
When I put the DC voltage here.
Yeah.
Yeah.
Does it do anything to the magnetic field of the inductor?
No.
No, why not? What's not happening? It's not the current, it's the
Yeah.
what of the current.
The direction of the current.
No. What's happening to the current here? Why do you need Q2? VCC is DC, right?
Yeah.
So why do you need Q2? Why not just let VCC float around? Wouldn't that work?
No. The voltage won't build up.
Why not?
Because the inductor needs on and off for it to.
So, so what's the technical term for on and off? It needs the current to,
It needs the current to flow. And
no, we came to the conclusion that if the current just flows, nothing's gonna
Yeah.
happen. Why do I need Q2 there? As it turns on and off, what's it doing to the current?
it dictates where the current would flow.
No, not really. But look carefully there. If you look at the rest of your circuit there, you have a pretty high impedance branch going off there.
Mm.
So I don't think that's. In fact, it's so high impedance that if you try to draw a little bit of current from it, it drops the voltage. What do you need the current to do? You're right, it's on and off. What is that? What is the current doing? On and off, it is, I said delta I. What does that mean? Delta I and delta T. DI and DT.
Yeah, it changes over time.
It changes. It needs to have a current change, exactly.
Yeah, change.
So what happens when there's a current change? Answer Mr. Brown's question. If there's a current change, what happens?
The voltage would increase.
Yeah, there'll be a voltage there
Yeah.
because of the current change, right? That's why you need that oscillator to make the transistor. Then what happens?
Then when the current changes here, it would build up voltage.
How much?
And,
How much of voltage will it build up? Just a little bit?
yeah, no. It depends on the duty cycle of my oscillator.
Yeah, because we're changing what? The duty cycle is representative of a change of what?
Change of duration of pulses.
Yeah, which is a change of?
Which is the change of on and off of this.
Which is the change of?
Of current.
There you go. So it's how fast your current's changing, right? Yeah, it's all a function of how fast the current changes. If the current changes very fast, the inductor tries to prevent that from changing by creating what? A voltage.
Voltage.
What kind of voltage? Is it just going to be
Induced
the
voltage.
9 volts?
Yeah, the induced voltage from
Yeah, but it's just going to be 9 volts?
No, it will add up to the induced voltage of the inductor.
A little bit, sorry?
It will add to the induced voltage of the inductor.
Okay, so how much will that?
And also with this.
Okay, so how much will that induced voltage be? Will be very small?
Very big as compared to the BCC.
So how big? What value?
What value? For my circuit, it goes up to 500 volts.
There you go. There you go. So what kind of converter is this? This is a DC to DC converter.
A boost converter.
Boost converter is a very simple boost converter. What is its drawback though? It has a somewhat of a problem. When it has a high voltage there across R7 and C4 the ground, which is C3 the ground, okay? It has a high voltage, but what did you notice happens when you try to measure that voltage?
Yeah, because it has a very large voltage, so the current is too small. And my multimeter, my measuring equipment like the multimeter and oscilloscope in the lab, it draws a lot of current, which
Why? Why do they draw a lot of current?
because the impedance of the equipment is too small and
Compared to what?
as compared to R7
R7 and what else?
and
Yeah, there you go.
and my
Your
circuit, yeah, my
Geiger
Geiger
tube, right? So where does the current go then? If it's a smaller impedance across it?
if there's a smaller impedance across so it will,
It goes to.
it goes to the device,
to the device, right?
multimeter, so.
And what's the regulation on your boost converter here then? It's very good or very poor?
Regulation.
Maintaining the voltage, is it very good at maintaining voltage or is it very poor when you load it down?
It's very poor.
Very poor because the current gets drawn into the meter and the voltage drops, then your Geiger tube doesn't work anymore, right? So you couldn't measure it directly like that. What did you have to do to measure it?
I I connected a very large resistor, which is a 1 gig resistor, from this in order to form a voltage divider from my meter and the 1 gig resistor.
There you go. Where'd you get a 1 gig resistor? I don't think Digi has any.
Yeah,
Did you bought a 1 gig resistor?
yeah.
Really? All right. I would have taken a few meg ones and just put them in series first. It's probably a lot cheaper. All right, so then you now have a high voltage on pin 1 of the Geiger Mueller tube there.
Yeah.
Okay? And a ionization particle comes down and strikes the tube. What happens?
It produces like a short here because
How
of
come?
because the tube or the
What's inside the tube?
inert gas, electrons and
No.
electrons.
Inert gas, an inert gas.
Yeah.
Okay? So you have a high potential voltage across the tube and this
Yeah.
particle strikes the gas. So what
Yeah.
happens?
It separates the electron from the gas,
Okay? And then what happens?
and then so this is positive, heavily positive, so it will attract the
No, I wouldn't.
electrons
No.
that would create.
What happens to the gas when it gets,
It breaks down.
it breaks down? So that means it becomes what?
Electrons and photons.
Yeah, but it becomes what electrically?
Electrically, it is it conducts.
It conducts. So you get a bit of conduction as the energy from the
From the
particle strikes, and that goes away, right? So you get a little blip that you were able to see on your scope results. But why wasn't that enough?
Because the conduction is too fast. So
How fast?
About microsecond.
Microseconds?
5 microseconds.
Yeah, you measured it? 5 micro?
Yeah.
Yeah. So fast sometimes it doesn't even trigger the
Yeah.
scope, eh?
Yeah.
And so what do you do to fix that?
I have a pulse stretcher here.
Yeah, so use a stretcher, yeah. I
Yeah.
wish we could have talked about that, but it's all right. All right, thank you. Thank you.
I know. Well, between L1. Very interesting. Yeah. That's right. You need the right probe for that.
As a friction.
Yeah, I know.
I've heard cases I guess the old saying, money can't buy the love. But yes, it is a deal. Yes, absolutely. That's what it comes
And
to.
actually, the next line is, money can't.
No, I was listening to it yesterday.
Yeah.
Sir Paul McCartney.
Yeah.
Yeah, but she would have, that's the other thing, is that you marry a rich person, divorce. A lot of money. Well, no, because the question would be, would it be her
Good job.
It's amazing how much time you
Yeah.
You're giving myself, right? I'm giving no, I see where Bill says nothing.
Yeah. I know. There are lots of more people.
Charlie? Yeah, I just thought that.
Yes.
So the next.
She's doing one gig.
They're not even expensive.
Hold on, they're not available. Let's see if it's going to do. Price 92 cents.
Well, that's
That one's 5 cents. I don't know what the difference is. Well, it's the mounting for one. I'll use it.
yeah.
At the beginning, I was using numbers.
I was using beta, but like machine.
Sometimes you see question mark, that means I don't know what to say.
I put a question mark in because I don't know what it is.
That's the whole page.
there's the highest resistance in green, 500 units, but zero is.
They only cast it on
There's only four resistance.
Oh, yeah, exactly.
Writing is kind of like that when you're training writing.
They only cast it on demand.
Yeah, probably.
Oh, they only get
Yeah.
It's got such a high
Because you can
resistance.
give a lot of different feedback.
I didn't know
I want
what
the feedback to be as effective
and price.
as possible. And that, I find that to be challenging.
Yeah.
Writing comments. We have this problem that I think that writing is very
Yeah. In English?
yeah. It's a skill.
One of the few things I've worked pretty well. I mean, there's still room for improvement. Yeah. Not your. So the goal there would be, yeah, you
So we'll be here and then just say,
Right.
That's right. And then write something.
Yeah.
I was.
It's coming to
It is. That's right. You need the slow.
Yeah.
I tried that.
I don't use it all that often, but it still needs to be. I wasn't.
It wasn't very good.
It's the typo.
Not eating doesn't work. The don't sign just speak to
Exactly.
I tried on last
Our body is too small.
Yep.
Thank you for.
Yes, you can.
Yeah, you can.
Yeah.
On. So I wrote the giant K, on. Yeah. And I sent it, and I just wanting so then I sent another email saying, you know what, when I went through my cover, I noticed there were a couple of typos. You mind if I added
Physical work.
Yeah.
Because your eating habits, probably didn't change.
Because it just kind of sticks out.
Your appetite's probably.
one time.
So then you're.
Before I came here,
more than
like email.
I did that.
Like to get accepted.
Yeah.
So it's like kind of using same format, like just
You know,
Yeah. 1 year here.
But much I send it to another.
I noticed my review that year. So my input increased. She back. They hired her back at Good.
I saw her.
I should have got that like.
Yeah, that's the type of person.
Yeah.
All right.
Okay, so time for the last presentation of the day. So, and it's from Maricel Tapiriren, right? and it's about multi-zone solar powered watering system. But before I give you I don't know how to say that in English. Yeah. So after the presentation is done and the questions, then we have to go to the lab A2215 for demonstration.
Yes.
Okay, go ahead.
Thank you, Mr. Salan. Good afternoon, everyone. My name is Maricel C. Tabiliran, a student of Electrical Engineering Technology Department, under the supervision of my great advisor, Mr. Broad. My project, I'll be going to present my project, Multi-Zone Solar Power Watering System. The following are the contents of my presentation: introduction, components used, block diagram, wiring diagram, testing and results, advantages and disadvantages, application, future expansion, conclusion, and references. Introduction. As a human being, we need food and water to survive. So plant need water to survive. So farmers have a big role in the community. They are the one who bring food to our table, like vegetable, fruits, and crops. And those plants need water to be grown. So my project, multi-zone solar powered watering system, is very suited in this field. Multi-zone solar power is a watering system that watering application system used to water the plant. It is multi-zone. It's because it is used 4 zones. Then it is uses to grow plants and landscaping. It is replaced the old process of watering. It's because in this era, in technology, people are very busy. In the new world in our new world, busyness is the trend. So technology invention like cellular phones, internet, automations give us the busyness in our life, and sometimes we forgot what is really important. Especially to be a good steward to the environment. This project, entitled Solar Powered Watering System, is involved the application of technology for environmental purposes, specifically in automatically be used in watering the plants without any human intervention. Meaning to say, it is automatic. This project uses solar panel as a main source to energize the water system. Programmable logic control to control the schedule of watering. And along with the moisture sensor to sense the moisture level of the soil. Meaning, this device is worked by schedule and the condition of the soil. It is only working within the schedule of watering. For example, this day you want to schedule of watering is 6 p.m. until 6:05. 5 minutes of watering every day. But there is one condition. It should depend on the dryness and the wetness of the soil. It's because why? What if it's rainy days? It's watered, the plant? No, because we waste water. That is why I set the soil moisture level. So if it's rainy day, and the moisture sensor is sense that it is wet, so even if it's schedule of watering, it will be cut off the process of watering. Okay, so that is why the purpose of this project is multi-zone solar power system is watering system that eases the burden of getting water to the plants when it's needed. The concept of this project is used to green energy to power the technology for the purpose of watering the plants in the backyard for without any human intervention. Ultimately, this system eases the burden of homeowner who wishes to maintain a garden by taking care of their watering needs as they go about their busy lives or out of town on vacation. So meaning, the owner have a convenience and a peace of mind that their plants is to be grown even without anything, so without any human intervention. So if you ask me why I choose this project, way back home in the Philippines, when I was young, my father is a farmer. So we are doing the old watering process. When I come to Canada, still loving in plants. So that is why I explore on making this project without compromising my daily activities and my business in life. So that is why when I asked my instructor, can I make the watering like this? And he asked me, I want a PLC and I want a moisture level. A moisture of the sun. So I think that, so I like this one and I want to use this one because this project is ready-made. You can use it anytime in your home. Okay. So moving on, we have our components used. The major components that we are used in this project is the solar panel, charge controller, circuit breaker, battery, and soil moisture along with the soil moisture controller. This one you need to adjust from high or low. The high for this one is 60 to 100 and the low for that one is 60 to 0. Meaning to say by high, that is wet soil. Meaning by low, that is dry soil. So it's easy for the PLC to understand what is high and low. Okay, PLC is program the scheduling time. So I use that one, Siemens Soft logo, because there is a real-time settings. We can set the time. Relays. The function of the relays in my project is to enable the system, and also some other relays is to control some bulbs. And we have our solenoid bulbs that is used for us to watering, and some other materials that we are using is dripping hose. Moving on to our block diagram. I will split into two. My block diagram is split into two. So this is the first part. So this is the PV panel. The sun going to our PV panel. So going to the solar charge controller. So PV panel is the one who capture energy coming from the sun. And solar controller is the one who regulates the voltage going to the battery and to protect the battery for overcharging, then to the circuit breaker. Our system is 24 volts. So this is our second part of a block diagram. So as I said, this is 24 volts system. All our devices here is 24 volt system, including the push button, relay, indicator, bulb, sensor, PLC, and the 4 relays, and also our solenoid bulb, including the indicator bulb. Going back to our block diagram. So push button, this one, if you push in the push button, it will enable the system and send signal to the PLC that this is the time for operation. This is time for the automation. And if you stop, push button stop in, it is the time to stop the operation and indicate the off indicator. And also for this one, I forgot, if you push the start, it will also enable the system and send signal to PLC, and meaning to say it's on, the indicator will be on. This is the green light when we see the actual project. We can see here, we have our soil moisture sensor. This is 4, it's because this is 4 zones, 4 beds. So for example, the soil moisture sensor will send signal to PLC that the soil is dry, so it's time for watering. Meaning to say, it is watered in the scheduled time. So we will set the programs with 3 requirements, which is we on the system, and the second one, the scheduling time. If they meet the schedule, a time to water, and if meet the conditions of the soil, which is the dryness and the wetness, it will water. So if it's wet, it will automatically cut off the operation even if it's scheduled time. Okay? So next, if the PLC is meet all that conditions, the scheduling time, the condition of the soil, it will be energized all our bulb here, and this is called our control bulb, which is command to the solenoid that's open and need time to water the plants. And also, our indicator bulb, when one of them are working, they are also indicating that someone are working. Okay, so for example, this one is working and all of them are not working. Still, this bulb is indicating that there is still working. Okay, so this is our block diagram and this is very straightforward. So maybe moving on to our wiring diagram. So this is our wiring diagram. So this is our PV panel. So it's very needed that you know the polarity of each of them. So we have positive, negative going to charge controller. Then positive, negative also to our battery. So and our circuit breaker. So when the PV panel captured the energy coming from the sun, it will coming here to the charge controller to regulate the voltage going to our battery. And then also we have our connection here going to our circuit breaker, the one. So if we energize or we will on the circuit breaker, we have also our positive and negative, and I put here a terminal block. Also here I put terminal block, I don't know if it's correct, so yeah, maybe. So all our devices here is 24 volts. So first, this is our PLC, and the PLC also same like the other devices that need a 24 volts DC supply. So the L1 is the positive one and the M1 is the negative one. And our input is namely, we have our relay R5, and we have our sensor 1, 2, 3, and 4, and we have our also a soil moisture controller, which is our soil moisture sensor attached here going to the PLC, so that it's easy for us to programs and command the PLC what to do. Okay, so this is our input and this is our output. We have our output here, so I have a correction for this one, R1, R2, R3, R4. This is the load going to this side. Now I will be going to explain for our schematic diagram, wiring diagram, sorry. So for example, we will on the PB2. So it will be energized the R5, and the first one, this open, will be closed. And this one will be lights on. So next, R5, it will be closed also, meaning to say it's time to start the operation. It's time to start the automation. So start. Okay, so it will send or it will trigger the I1 to send signal. So next, for example, we will off this one, automatic, this second rung will be open and off these red lights. Okay, so assuming that we on the process, we are now on the automation process and we will start the automation. The first requirements, when I study this one, there is a 3 requirements. We need to on the process. The second one, we need to meet the schedule time. And the last one, we need to know the condition of the soil, which is the dryness and the wetness of the soil. Okay, next, assuming that we will on here the PB2. So it will energize this one and also this one, send signal. So once the soil moisture also, the first one, we on already. And once the PLC meet the requirements of a scheduling time, for example, 6 p.m., now is 6 p.m. So the next requirement, the soil, it should be dry, meaning to say it's time for watering system or watering time. Okay, so this one will be closed and Q1 will be energized and close this one and send signal to the solenoid valve that's open and it's time to water. Okay, next, for example, this one, this sends that the soil is wet. So it is not closed, it will still open, and this one also not energized because the soil is wet. No, it is not time for watering, so this one is not watered. Next, this one, the next soil moisture level or soil moisture sensor will be sense the dryness of the soil. It will close again and it will energize this one and it will close this one and water the plants. Okay? So next, for this one, for I5 or our sensor number 4, it will dry. So for example, it's dry. So this one is energized and send signal to the solenoid 4. So all our zone now is they have working, dry, and wet. So meaning to say they are working, not working, working, not working. So this system is working by schedule and the condition of the soil. Okay, so this we already met the 3 conditions. Okay, so now here we have our yellow lights which is connected to this one, R1, R2, R3, R4. So meaning here, if there is some of them are working, still this yellow one is working. Why? They are all series connected. Okay? So that's it, my wiring diagram. Okay, so moving on. So yeah, this is the working principle of each components. So the PV panels collects the energy, I already tell this one, from the sun to store the battery to energize the system. Charge controller to regulate the voltage going to the battery. Circuit breaker protects the system from the possibility for overloading and short circuits. Push button, stop and start, used to start and stop the automation process. Relay 5, used to enable the system. Send signal to PLC when it's time of automation begin and power on the indicator bulb. Soil moisture sensor measure the level of the moisture in the soil and send signal to the PLC if watering is required. Then PLC is the one who programs the scheduling of watering and receives signal from the soil moisture sensor for moisture level of the soil. And relay 1, 2, 3, 4 is control the running operation of the solenoid valve. So moving on to our testing and results. So this test is assess the functionality of the project. So the first one is the volumetric flow. So the volumetric flow is measure the maximum amount of water that acquired in the minimum minutes. So for example, we can measure the volume of water within 5 minutes. So the first thing we did is to supply again the system and set up the PLC in manual settings for the time. So for example, 6:05, 6, then 6:05, 5 minutes of watering. And then, yeah, if the time is already there, 6:05, and the condition of the soil is dry, it's time to water and prepare the bucket 1, 2, 3, and 4. And this is our results for this one. So I'll make this one in the Excel. So the first nozzle 1, 2, 3, and 4, this is signifies that each zone have each dripping hose. So they have also nozzle there, 1, 2, 3, and 4, and each of them acquire 4 liters in 5 days. This is constant, and they have some are 4.5 liters. They are measured by cubic meters per seconds. So there is also factors that we need to consider for this one. It's because the nozzle is need to be adjust half or full. But when I did this one, I used the halfway through opening the nozzle. So meaning to say, there is a factors to affect how much water acquired when you adjust the nozzle. Okay? So this is the first test that I did in my project. And the second one is the battery longevity. This one is to measure the lifespan of the battery on the required time, or not required time. So it should be run in the long time. That can be energized the solenoid A, B, C, and D. But this battery longevity is, I'm not fully done this one because the time constraint, we have running out of time to do that one. So I'll make a test for this one, but it's hard for me because the battery is full charge. So I did not do that, so that is why it's very difficult to do it. So I already used for this one 5 days for 2 hours, including the testing and functionality. And still, the battery is in 3/4, but I have no any data on this one. This is only estimation. It's because we cannot measure the state of charge. So I need more days to fully drain the battery to better observe the lifespan of our battery. So based on my computation, on 5 minutes each day, it will take 27.7 operations. So these are the figures here down. So in 5 minutes, we have our load, 572 watts. Our system is 24 volts. And times by 5 minutes over 60, I got 1.99. Our battery bank is 55 amp. So I'll divide this one. We have 27.7 times operation. So this one is, I think, when I convert it into this, 1 day and 3 hours. So we will run the system in 1 day and 3 hours. It's because our system is only run 5 minutes. 5 minutes in 1 day because we will water only once a day. So as you can see, the volumetric flow, this is 4 liters is very much. It's too much. That is why if I am the owner of this one, I cannot make 5 minutes, maybe 2 minutes or 3 minutes because this is overwatered. Okay, so that's it. And the advantages and disadvantage. Disadvantage because only one I put it. So disadvantages is minimize the human intervention. Then work according to schedule and soil moisture level. Minimize the wastage of water because you are the one who minimize the water, or it is the reference of the owner how many minutes they want to water the plants. Okay, so they are the one who know how much water. So disadvantage, costly due to insulation. Why? I use solar panel and battery, but yeah, my solar is sponsored by Mr. Ledger, but the battery is not sponsored, so it's too much. So that is why the the cost insulation is high. So other disadvantage maybe is there are some minors troubleshooting on this one happen, so it's okay, but it's minor. So I don't put in the advantage only, okay? So the application is, we can use this one in home garden. It ready made to use. If you want to replicate my project, we can do it. Okay, so lawn gardening. So we can use this here, and indoor farmings and agricultural farmings. It's because I am lazy to water my plants, so that is why I want this one. Okay, so future expansion, the project can be innovated by adding bigger ponds to accommodate bigger space like farm, lands, greenhouses, and flower beds. Then the conclusion, so the conclusion, the device is fully functional. Large garden are benefits greatly from the system. Automatic operations, lessen the needs of manual labor, relies less on conventional energy sources by using solar energy, which is renewable. So it is eases or minimize the burden of the homeowner, because this is without any human intervention. This is automatic. Okay, so this one, the project needs to be tested in actual field in a long period of time to test the effectiveness, durability, longevity of the battery in order to check concrete result in the future improvements of the project. Acknowledgement, I would like to acknowledge to my husband to support me, and I would like to acknowledge my friends and classmates to always there for me, to my instructor and my advisor, Mr. Broad, and also to my Mr. Ledger, who always lend me all the materials to materialize and everything, and to Mr. Kodai, who always patiently checking my documentation. Thank you very much. And this is my finished project build. This one is the image front box, and this one is the setup PV battery charge of the controller, and this one is the setup of circuit breaker, PLC relay, and power supply, and that one is the setup from solenoid bulbs to the soil moisture sensor. So references and everyone, thank you.
What type of moisture sensor is used in this project?
The type of sensor that I use in this project is a humidity. I don't know if it humidity rather.
Humidity sensor.
Yeah, I ordered this one from China.
Well, I didn't want to know where you ordered it from. I want to know what type it was.
This type is. I'm not sure for the type of my sensor.
Because there are 5 main types, and I just wanted to know what type yours is.
Humidity sensor. The other one is
moisture
the
sensor
content level of the soil.
A moisture sensor and a humidity sensor are the same thing. Okay.
But this is the moisture sensor because we are measuring the dryness and the wetness of the soil.
Yeah.
So,
but I want to know what type.
Moisture sensor, sir.
No. What type of moisture sensor are you using?
What type of moisture sensor? There is a type of moisture sensor. I think.
There's 5 types, yeah. Which type is yours?
Moisture sensor level. That is moisture, sir, because I need to measure the moisture level of that sensor.
No, but my question is, what type of moisture sensor is in use in your project?
What type? Level moisture sensor. I will think what is that sensor because I am the one who buy that. I didn't see
Some
that.
examples are FDR, TDT, neutron moisture sensor. There are various types. I just wanted to know what type yours is.
Neutron. I did not check that.
Okay, so you don't know?
So yeah, sorry for that because I only check the level of my moisture. So it will measure the dryness and the wetness.
They all do that, but there are various different methods of doing that. So that's why I was curious to know if you had done any research into that and
I
the
had
type
a
of-
research on moisture, but I don't know what is the type of moisture. So I just only check in the market what moisture fit in on my project. So that is why by the way, I buy 5 moistures on that and only 1 fit in. So that is why.
So I guess we got your answer there. Can you take us back to your test results?
Yeah, that's it.
Yeah, like how do you explain the difference in the volumetric flow for nozzle 1 on days 2 and 3?
Okay, days and 3. So, 2 days and 3.
Yeah.
So in 2 days and 3, I don't know if the nozzle will move the adjustment. So that is why I got 4.5 or any other factors. Maybe I will make the posit more adjust the hole. So that is why I got 4.5. So sometimes that factor will affect on that. It will accumulate the water much if the adjustment of the nozzle is more than like that. So it's half or full. So
is that?
yeah,
that's,
maybe on that time.
Human error then, or is that what you're saying? It's human error? Introduced
Yeah, maybe because I did not use that one in the whole day. Maybe someone or I touched that one. I will tour that because only nozzle 1 is different of them. Okay, so the other one is same. So sometimes there is a factor in that.
Anybody else have questions on the test?
Why did you express the test in scientific notation?
Yeah.
That's I use that one Q V over T, volume over time.
No, I didn't ask you how you calculate it. Why is it expressed in scientific notation?
Yeah, I just only put like that. I don't know. So
What notation are we most used to?
What would
in
make this
engineering?
easier for us to read?
Yeah.
we just only use the 13 point something. We are not using the 10 to the some third.
Well,
So
no, I would hope you use, well, you don't rearrange the values, but, so 13 point something in what?
Meter cubic per seconds.
No, you can't just say 13.3 meters, because that's a totally different value than 13.3 times 10 to the minus 6 or 5, whatever it is.
I can't actually tell what it is.
What other notation do we usually use in engineering besides scientific notation?
Other scientific
In fact, this is
notation.
incorrect scientific notation, by the way, it doesn't follow scientific notation
No.
requirements.
It's actually a blend of.
Other scientific notation we are using is engineering notation.
Would
Yeah.
metric
Yeah.
prefixes?
With the prefixes, yeah.
That's,
That would have made it much easier to interpret the numbers here.
Very important.
Any other questions on the test?
A lot of questions on the wiring diagram.
Let's go, we can go to the block diagram. or
Sure, block diagram.
Block diagram, yeah, block diagram. Okay.
Go back.
Maybe
The other one.
the more inclusive one there, or the one, yeah. Does the start push button actually provide functional flow to the stop push button?
This one, sir.
Yeah.
Other legs of this start button is connected to
I know
stop
it's
button.
connected there in the wiring diagram, but functionally, does the start push button provide input to the stop push button?
No, sir. No, sir.
So how should it be shown here on this block diagram?
I just concluded that when they have some connection to other components, it should be connected. So that is why I put the R.
No, but that's a wiring diagram.
This is
block
not a
diagram.
wiring diagram. It's a functional block diagram, okay? So answer my question now. How should this be represented?
There is no arrow on that one, on the push button. So it will
What do
directly
you
to
mean
the
there's no
enable
arrow?
system.
I see an arrow leading away from it.
Here,
Yeah,
yeah, so if I corrected this one, I cannot put this one here. It will be connected direct here.
yeah, right.
Yeah, so just only my thinking that if there is a connection between one component to another component, so I put that arrow.
Yeah, but it's not about that here, right? Okay, yeah. Any other questions on the?
Your on indicator, off indicator there?
Yeah, this is the off indicator and on indicator. It's because if you push this
No,
one,
let me ask a question, okay? Okay. Your on indicator and off indicator, again, systematically, does that, the enabling of those come from the enable system? I don't even know what that is. The enable system block?
The reason you don't know what it is, what's R5?
R5 is that is a relay
Yeah, but
enable system.
R isn't the symbol for relay, right? It's resistor in our world, right?
RLY is our,
Well, what's the typical symbol for a relay?
that is a coil. We will put the coil.
No, but I mean alphabetic.
Alphabetic, we use the RLY for relay.
There's a better one. Do you know what it is?
Yeah.
You do?
Ah.
If you do, tell us what it is.
This one, R5.
R is resistor.
R is resistor.
Yeah, sorry.
So what's the
R
normal-
resistor, R.
What's the normal alphabetic character that's used to represent? relay in our world?
That is RLY5 for relay.
Not typically. It's normally a single letter
Relay.
reference, yeah.
C,
C would be what?
coil.
Capacitor, right?
I know.
Yeah. What's relay normally?
The X,
Not X, no.
same as K.
K, right?
K.
Yeah. Normally. So if he saw K5 there, then he would know that
Okay.
that block is an actual relay. Okay. Does that answer your question? Sure.
I give it to you,
Now you
Mr.
can ask
Rhodes,
your next
so many
question.
times.
Well, the arrow confuses me then, because if it's a relay, are those push buttons actually controlling the relay directly, or through the PLC?
Yeah, they are.
They are directly?
Yeah.
Okay.
Yeah. Any other questions on block diagram?
No, you
Okay.
asked mine.
Let's go to the, oh, sorry.
I know.
Would you like me to retract my question? Let's go to the schematic, or the wire diagram? Yeah. Okay, go ahead.
Correct me if I'm wrong, but is it standard to have the ladder logic in a wiring diagram?
Not so.
She has ladder program too, but she didn't show, you didn't show your ladder
Yeah,
program, did
we
you?
have. I will show you.
Okay, hold on, just wait, let's just go with his question.
Yeah, question.
Yeah.
Well, that was my question. Is it standard to have?
Because I answered the question of Mr. Ledger. It is not a ladder diagram itself. It's because I will show the contacts of the per coil. So if I put that one in the same as normal diagram that we use in the PLC, I will just only write the K1, K2 like that. So but this one, in order us to better understand, I write this one. I write this per coil.
Okay. I'd like to follow up though, R2, R3, R4,
Yeah, that is why I am wrong, because that is K1, K2, K3, like that.
That's
So-
fine, that's fine. And since you have designated as R1,
Yeah.
R2, R3, R4,
Yes.
where the cursor is there.
That is K1, K2, K3,
Yes, I
K4.
understand that.
Yeah.
We got that, we figured it out. So K2, K3, K4 now, okay?
Yeah.
How are those wired electrically?
Yeah, that is wired by pins. That relay have 14 pins. So I'll use for the open contact, which 5 pins.
Okay,
Yeah.
let's go back to, so if this was in your first year circuits class, and we asked you what configuration is this wired as, what configuration would it be? Series or parallel?
Parallel.
Okay, because during your presentation you said they were series connected.
No, only this one here.
What? What's that? That's a piece of wire. I don't know what you're talking about series there.
Sorry.
Where is series connected in that?
No, parallel.
Yeah.
You referred to, you said a lot actually about this device or component sending a signal to another component. What kind of signal are you talking about?
In what component, sir? Here in PLC?
Well, I don't recall which component necessarily. I mean, we can go back and look at the video.
We have our programs we made, yeah, and then if that programs is already started, so if, for example, this one is start, yeah, so when this one is start, it will be closed and it will trigger here that it will start for automation. So it's sending message that it's starting for automation. That's it.
Okay, so
That's what I understand on the PLC.
Okay, so you said it would send a signal, or now you're saying, you changed your term, you're saying it sends a message.
I don't know, signal, sir, signal.
Is it a signal?
Yeah, signal, sir.
What type of signal is it? Sine wave, square wave, triangular wave? What kind of signal is it?
Meaning to say, if it's signal, there is a voltage that coming on that side, and
Okay.
he detect that now it's time to start. It's because I have already voltage coming in or current coming in. So okay, so start it like that.
So it's not a signal. Really, it's what is
sorry
it?
for
What would be a more appropriate term?
What correct upward? Signal, load signal. I don't know what signal. What appropriate signal is that? Frequency signal like that, or
Well, is it a frequency?
Hertz like that.
Is it a frequency? What's the frequency of these signals?
A frequency, we know that in AC we have 62.
Okay, is this
Yeah,
AC?
No, that
What
is
is
DC.
It's DC?
DC, yeah.
Okay,
Voltage positive signal.
so is
Coming
it,
from-
well, that's my question, is it a signal then?
Signal.
What's a more appropriate term to use there?
What signal is that? Because I just only heard signal, I think.
Well, it's actually two different levels, really, isn't it? What are the two levels? What if the switch, you're using a switch symbol there, where your laser pointer is feeding input 3 is open? What's the level that's present on input 3?
Sorry again, input 3?
Yeah, your laser pointer is sitting on input 3, so I thought we'd use that one. Okay, input 3. If the contact connected to input 3 is open, what's the level that's present at input 3?
Open? So open is 0, no signal.
Well, you're calling it a signal again.
0.
It's not no level. It is a
No.
level of
Level
Of what value?
of 0 or 1?
Zero. Zero what?
0 or 1 false or true.
Zero. What's the other extreme? It's either 0 or
0 or 1.
Electrically here, right? If the switch closes, what's the level that's present on input 3?
If close,
Yeah, if it's closed.
if it's close, it's 0. It's because they have, yeah,
Well, you told me
If
it was
it's
0.
open-
You told me it was 0 and it was open.
1.
No, let's talk about electrically though.
Oh,
You
okay.
gotta use units with your, right?
Yeah.
So what's the other level if the switch is closed?
Other level,
Mm-hmm.
2, 1.
Electrically, what level would it be?
If it's close, yeah?
Yeah.
So if electrically close, we can measure that 1 0 for resistance or what? 1.
Well, I was thinking if your project was active here and the switch connected to input 3 closes, what would be the level seen at input 3?
Level same in input 3.
Yeah.
I don't understand the question. It's 1.
In what units?
There is limits.
Yeah. We're talking electrical here, right? This is an electrical device.
High or low? Like that?
If I measured it with my multimeter, what would I see?
Ah, okay. So if you measure that one in multimeter and that is close,
Yeah.
yeah, close 0 resistance. If this is
Do you
closed, if it's
measure-
open, that is open.
Remember we said that this is active, that this is in use, okay?
Ah, an active.
Am I gonna measure resistance?
No, you cannot measure
No.
resistance on
So what
that
am I
one.
measuring then?
So we will measure that voltage.
So what am I gonna read?
You're gonna read something.
Yeah, that's what- I know that, I want you to tell me what I would read there.
So if that is 24 volts, there is 24 volts on that one.
So if the switch is closed and I'm measuring at input 3, I'll measure what voltage?
24 volts.
24 volts, okay?
Yes.
And if the switch opens,
We cannot open. We cannot open. We cannot.
you can't open it?
We cannot measure that one. It's because it's open. Yeah, but there is
What do you mean? I could measure it. What will I measure?
0.
0.
Yeah,
0
0.
what?
0 voltage.
0 volts, right?
Yeah.
Okay, thank you. Are we at a time? Yeah. Oh, okay. Okay, we gotta proceed to the demonstration.
Hold on, I'm gonna take attendance, don't move.
Oh my God. Killing thing.
Jonathan? Jonathan? Hey!
Present.
I don't hear your name, you're not gonna be here. Jay?
Here.
Nathan?
Aye.
Adam? Oh, no. Brian?
Here.
Aljon?
Here.
Dearford? Alejandro?
Here.
Arpit?
Here.
Juan?
Here.
Jake?
Here.
Guillermo?
Yes, sir.
Benjamin? Matthew? Oh, sorry. Giovanni?
Present.
Jose?
Here.
Heber is here, right? Dawson? Dawson? No. Graydon?
Here.
And one last thing. There is a survey on SPL2 Please fill it out before Monday morning, 8:25.
Survey?
Yeah, it should work now. I forgot to make it visible. Okay, so please fill it out as soon as possible, really. Okay? Thank you.
I was supposed to be time window, so that it wouldn't water in the whole thing.
All the players you need, you can all of these stuff.
But they're hard to do. Yes,
Wherever he announced at the beginning of
Hey,
See how you don't pay attention? Yeah, you're the surfer.
I think you should learn more